The Speed of Light, a bedtime story of the universe's ultimate speed limit. The light that touches everything. Close your eyes for a moment and imagine the very first light that ever touched your face. Perhaps it was the gentle glow filtering through hospital windows on the day you were born. Or maybe it was sunlight streaming through curtains as you opened your eyes as a child, wondering at the golden dust motes dancing in the air. That light, every photon that has ever caressed your skin, illuminated your path, or painted the world in colors before your eyes, has traveled an impossible journey to reach you. It has raced across the vast emptiness of space at a speed so fundamental to our universe that nothing, absolutely nothing, can surpass it. Not the fastest rocket we've ever built, not the most energetic particle hurled by cosmic forces, not even our wildest dreams of interstellar travel. This speed, 299,792,458 meters per second, is not just fast, it is the fabric from which space and time themselves are woven. Tonight, we're going to follow the gentle path of discovery that led humanity to understand this ultimate speed limit. It's a story that spans millennia, from ancient philosophers wondering about the nature of sight, to modern physicists peering into the fundamental structure of reality itself. It's a tale of curiosity and wonder, of minds that refuse to accept the obvious, and of revelations so profound they changed our very understanding of what it means to exist in this universe. So settle in, let your breathing slow, and prepare to journey through time and space as we uncover the mystery of why nothing can go faster than light. The ancient wonder of sight. Our story begins over 2,000 years ago in the warm Mediterranean sunlight of ancient Greece. Picture the marble columns of the Lyceum in Athens, where brilliant minds gathered in the late afternoon shadows to debate the fundamental nature of reality. Among them walked a man whose curiosity about the simplest things would echo through the centuries, a man named Empedocles. Empedocles had noticed something that most people took for granted: the simple act of seeing. As he watched the fishermen's boats return to harbor at sunset, their white sails catching the last golden rays of the day, he wondered how his eyes could perceive something so distant. What was this mysterious connection between his vision and those faraway sails? In his contemplative way, Empedocles proposed something remarkable for his time. He suggested that our eyes themselves emit rays of light, like invisible fingers reaching out to touch the world around us. When these eye rays encountered an object, they would return to us carrying the image. It was a beautiful, poetic explanation that felt intuitively right. After all, didn't it seem as though our gaze could reach across vast distances instantaneously? But even as Empedocles developed this theory, other philosophers began to wonder about something more fundamental: the speed of these mysterious rays. Could anything truly travel instantaneously? Was there such a thing as infinite speed in the natural world? Aristotle, walking through the olive groves outside Athens, pondered this question as he observed the interplay of shadow and light filtering through the leaves above. He concluded that light must travel instantaneously. After all, the moment the sun appeared over the horizon, the entire landscape was illuminated. There seemed to be no delay, no gradual spreading of light from east to west. To Aristotle's careful observations, light simply was, everywhere and immediate, like consciousness itself. But across the Mediterranean, in the great library of Alexandria, other minds were beginning to question these assumptions. The scholar Euclid, as he studied the precise angles of light reflecting off polished bronze mirrors, began to notice that light seemed to follow very specific, predictable paths. These weren't the random, mystical emanations that earlier philosophers had imagined. They were geometric, mathematical, almost as if light were following invisible highways through space. Hero of Alexandria took these observations even further. As he experimented with mirrors and prisms in his workshop, surrounded by the scent of oil lamps and the sound of scholars debating in the courtyard beyond, Hero discovered that light always takes the shortest path between 2 points. When reflected off a mirror, it behaves like a perfectly elastic ball bouncing off a wall. The angle at which it approaches exactly equals the angle at which it departs. These discoveries were revolutionary. They suggested that light, whatever it was, followed laws, consistent, predictable, mathematical laws. And if light followed laws, perhaps it had properties that could be measured and understood. Perhaps it wasn't as mysterious and immediate as their predecessors had imagined. The stage was being set for a revelation that would take more than 1,000 years to fully unfold.
The Islamic Renaissance and the First Glimmers. As the classical world gave way to the medieval era, the torch of scientific inquiry passed into new hands. In the great centers of learning across the Islamic world, in Baghdad, Cairo, and Cordoba, scholars continued the ancient quest to understand the nature of light, but with new tools, new perspectives, and new questions. In the year 1021, in a small chamber overlooking the bustling streets of Cairo, a man named Ibn al-Haytham, known in the West as Al-Hazen, sat in contemplative study. The morning light streamed through his window, casting geometric patterns on the walls, covered with his optical instruments, curved mirrors, crystal spheres, and carefully ground lenses. But Al-Hazen wasn't just observing light. He was thinking about it in ways no one had before. Al-Hazen had a revolutionary idea that challenged centuries of accepted wisdom. Unlike the ancient Greeks who believed our eyes emit rays to see the world, Al-Hazen proposed that light comes from sources, the sun, fire, luminous objects, and travels to our eyes, carrying with it the information we interpret as sight. This might seem obvious to us now, but in Al-Hazen's time it was a profound shift in thinking. But Al-Hazen went further. If light travels from objects to our eyes, then it must have speed. It must take time, however brief, to journey from there to here. This insight led him to conduct what may have been humanity's first serious consideration of whether light's speed could be measured. As he watched the moon rise over the minarets of Cairo, Al-Hazen wondered, when the moon appears above the horizon, are we seeing it as it is at that moment, or as it was some time ago? The question haunted him, because it implied something almost unthinkable, that the universe we perceive through our eyes might not be the universe as it exists in this instant, but rather a collection of images from the past, a cosmic museum of moments that have already passed. Al-Hazen's work laid the foundation for what would later become the science of optics, but more importantly, he planted the seed of an idea. That light, however fast it might be, was not instantaneous. It was a traveler, and like all travelers, it needed time to complete its journey. This idea would simmer in the background of human knowledge for centuries, occasionally surfacing in the work of later scholars. Roger Bacon, in his stone tower at Oxford in the 13th century, pondered similar questions as he experimented with lenses and mirrors. He, too, suspected that light had finite speed, though he had no way to measure it. The notion began to take on almost mystical significance. If light had finite speed, then the very act of seeing was, in a sense, time travel. Every sunrise was actually a glimpse into the past, every star in the night sky a messenger from ancient times. The universe revealed through our senses was not the present moment, but a complex tapestry woven from countless moments of the past, all traveling towards us at the speed of light.
As the centuries passed, this idea would occasionally surface in the writings of natural philosophers, but it remained more philosophical than scientific. It was a beautiful concept, but seemingly impossible to test. How could anyone hope to measure something as fast as light, even if it wasn't instantaneous? The answer would come from an unexpected source: the movements of the planets themselves. Galileo's flickering lanterns. The year was 1638, and in the hills outside Florence, two figures stood in the darkness, each holding a shuttered lantern. The older man, his beard now silver, and his eyes bearing the wisdom of a lifetime spent peering through telescopes at the heavens, was Galileo Galilei. His younger companion, a student eager to assist in yet another of his master's ingenious experiments, waited nervously in the cool night air. Galileo had been thinking about the speed of light for years. Unlike his predecessors, who approached the question through pure reasoning, Galileo wanted to measure it directly. His plan was elegantly simple. He and his assistant would stand on two hilltops, each with a covered lantern. Galileo would uncover his lantern first, and the moment his assistant saw the light, he would uncover his own lantern. Galileo would then measure the time between uncovering his lantern and seeing his assistant's response. As they began their experiment, Galileo uncovered his lantern, sending its warm glow across the valley. Almost immediately, it seemed, his assistant's lantern flickered to life in response. Again and again they repeated the experiment, moving farther and farther apart, but always with the same result. The response appeared instantaneous. Galileo was disappointed, but not defeated. In his careful notes, written by candlelight in his study later that night, he concluded that if light had speed, it was so fast that it could cross several miles in an instant, or at least in a very brief time. He suspected that the delay he was measuring was not the travel time of light, but simply the time it took his assistant to react to seeing the signal. What Galileo didn't know was that light travels at such incredible speed that it would cross the distance between their hilltops in about 0.00001 seconds, far too brief for any human reaction to detect. His experiment was doomed from the start, but his approach was revolutionary. For the first time in history, someone had tried to measure the speed of light through controlled experimentation rather than philosophical speculation. Galileo's failure taught an important lesson. If light's speed was finite, it was unimaginably fast. To measure it would require distances far greater than any available on Earth, or timing instruments far more precise than human reflexes. The answer, when it came, would need to reach beyond our planet itself. But Galileo's experiment did something equally important. It established that the speed of light was a legitimate scientific question, something that could potentially be measured and understood through careful observation and experimentation. He had transformed a philosophical mystery into a scientific challenge. As Galileo packed away his lanterns that night, he couldn't have known that the answer to his question was already traveling toward Earth from the distant moons of Jupiter, which he himself had discovered decades earlier. The key to unlocking the speed of light lay not in the hills of Tuscany, but in the vast clockwork of the solar system itself. The Dance of Io and the First Measurement. In the year 1675, in the Royal Observatory at Paris, a young Danish astronomer named Ole Romer was puzzling over one of the most peculiar mysteries in astronomy. For months, he had been carefully timing the eclipses of Io, one of Jupiter's moons that Galileo had discovered. Io orbits Jupiter with clockwork precision, disappearing behind the giant planet and then reappearing with such regularity that astronomers had begun using these eclipses as a cosmic clock. But Romer had noticed something strange. when Earth and Jupiter were on the same side of the Sun, closer together in their cosmic dance. Io's eclipses happened exactly when predicted. But as Earth and Jupiter moved to opposite sides of the Sun, farther apart, the eclipses began to occur later and later than expected. By the time Earth and Jupiter were at their maximum separation, Io was running about 22 minutes behind schedule. Night after night, Romer sat in his observatory, eye pressed to his telescope, watching the tiny moon disappear into Jupiter's shadow and carefully recording the exact time. The discrepancy troubled him deeply. Io wasn't actually changing its orbit. That would be impossible. Something else was causing this apparent delay. Then, in a moment of insight that would change our understanding of the universe, Romer realized what was happening. The eclipses weren't actually occurring later, they only appeared to be later because the light carrying the image of each eclipse had farther to travel when Earth and Jupiter were separated by the full width of Earth's orbit. Picture it this way. Imagine you're watching a friend wave to you from across a lake. If you row your boat closer to shore, you see the wave sooner. If you row farther away, you see the wave later. The wave itself hasn't changed, but the light carrying the image of the wave has different distances to travel. Romer's calculation was elegantly simple. Earth's orbit has a diameter of about 300 million kilometers. The eclipses were delayed by about 22 minutes when Earth was on the far side of this diameter from Jupiter. Therefore, light must take 22 minutes to cross 300 million kilometers. When Romer announced his findings to the French Academy of Sciences, the reaction was mixed. Some astronomers immediately grasped the profound implications of his discovery. Others remained skeptical. Surely light, the most ethereal and spiritual of phenomena, couldn't be constrained by something so mundane as travel time. But Romer had done more than measure the speed of light. He had revealed something fundamental about the nature of reality. Every time we look at anything, we are looking into the past. The sun we see in the sky is the sun as it was 8 minutes ago. The nearest star appears as it was 4 years ago. The most distant galaxies show us images from billions of years in the past. Romer's discovery meant that the universe revealed by our telescopes is not the universe as it exists now, but a vast archaeological record, with each celestial object contributing its chapter from a different era in cosmic history. We don't just live in space, we live in time, surrounded by messages from the past, all traveling toward us at the finite speed of light. This realization would have profound implications for our understanding of causality, simultaneity, and the very structure of space-time itself. But in 1675, Romer simply knew he had caught light in the act of traveling, and in doing so had revealed one of the universe's most fundamental constants. His measurement, while not perfectly accurate by modern standards, was remarkably close to the true value. He had shown that light travels at about 200,000 kilometers per second, within the right order of magnitude of the actual speed of 299,792,458 meters per second. For the first time in human history, the speed of light was no longer a philosophical question, but a measurable quantity.
The wave makers, Young and Fresnel. As the 18th century gave way to the 19th, a quiet revolution was brewing in the study of light. The question was no longer just how fast light traveled, but what light actually was. Was it a stream of tiny particles, as Isaac Newton had suggested, flying through space like microscopic bullets? Or was it something more mysterious, waves propagating through an invisible medium that filled all of space? In London, in the year 1801, a physician named Thomas Young was about to conduct an experiment that would fundamentally change our understanding of light's nature. Young wasn't initially interested in light at all. He was studying the behavior of water waves in his laboratory, watching how ripples spread across the surface of a shallow tank. Young noticed something fascinating about these water waves. When two sets of ripples met, they didn't simply pass through each other unchanged. Instead, they interfered with each other.
Where the peaks of one wave met the peaks of another, the waves reinforced each other, creating higher peaks. Where the peak of one wave met the trough of another, they canceled each other out, creating calm water. This phenomenon, which Young called interference, gave him an idea. If light were also a wave, it should exhibit the same behavior. He decided to test this hypothesis with an elegantly simple experiment. Young took a thin piece of material and carefully cut two parallel slits in it, so close together they were barely visible to the naked eye. He then shone a beam of sunlight through both slits simultaneously onto a screen behind them. If light were made of particles, as Newton had suggested, Young expected to see two bright strips on the screen, one behind each slit. What he saw instead was a series of alternating bright and dark bands stretching across the screen. Where light from one slit met light from the other slit in step, peak meeting peak, there were bright bands. Where they met out of step, peak meeting trough, there were dark bands where the two beams of light had canceled each other out. Light was canceling light. This seemed impossible if light were made of particles, but it made perfect sense if light were a wave. Young had discovered that light exhibits interference, just like the water waves in his tank. Light, he concluded, must be a wave phenomenon. But this raised a puzzling question. Waves in what? Water waves travel through water. Sound waves travel through air. If light is a wave, what medium carries it? Young and his contemporaries proposed that all of space must be filled with an invisible, ethereal substance they called the luminiferous ether, the light-bearing ether. This ether had to be remarkable properties. It had to be thin enough that planets could move through it without resistance, yet rigid enough to carry the rapid vibrations of light waves. It had to fill all of space, penetrating every crack and crevice of the universe, yet be completely indetectable to our senses. In France, a brilliant engineer named Augustin Jean Fresnel was taking Young's wave theory even further. Working by candlelight in his study, surrounded by optical instruments of his own design, Fresnel developed mathematical equations that could predict exactly how light waves would behave in any situation. His equations could explain not just interference, but also diffraction, the way light bends around obstacles and spreads into shadows. Fresnel's mathematics were so accurate, his predictions so precise, that the wave theory of light became virtually undeniable. But the more successfully scientists described light as waves, the more mysterious the ether became. This invisible medium had to be everywhere, supporting the propagation of light waves from the most distant stars, yet somehow remaining completely imperceptible. The stage was set for one of the most famous failed experiments in the history of science, an experiment that would ultimately lead to a revolution in our understanding of space, time, and the speed of light itself. The Great Ether Hunt, Michelson and Morley. By the late 19th century, the wave theory of light was triumphant. Scientists had not only proven that light behaves like waves, but they had also made increasingly precise measurements of its speed. The French physicist Hippolyte Fizeau had improved on Ramer's astronomical method by using a rotating tooth wheel to measure light's speed over terrestrial distances. Later, Albert Michelson had refined these techniques even further, measuring the speed of light with unprecedented accuracy. But there was still the nagging question of the ether. If light is a wave, and if all waves require a medium to travel through, then the luminiferous ether must exist. Moreover, as Earth orbits the Sun at about 30 kilometers per second, our planet must be moving through this ether like a ship sailing through an invisible ocean. This motion, physicists reasoned, should create an ether wind, a detectable flow of the light-carrying medium past Earth. Just as the sound of a train whistle changes pitch depending on whether the train is approaching or receding, light should appear to travel at different speeds, depending on whether it's moving with or against this ether wind. In 1887, in a basement laboratory at Case Western University in Cleveland, Ohio, Albert Michelson and Edward Morley set out to detect this ether wind. Their experiment was a masterpiece of precision and ingenuity. They built an interferometer, a device that could split a beam of light into two perpendicular paths, reflect each beam off mirrors, and then recombine them. If there were an ether wind, light traveling in the direction of Earth's motion through the ether should move slightly faster or slower than light traveling perpendicular to that motion. When the two beams recombined, this tiny difference in speed would create a detectable interference pattern. The experiment required extraordinary precision. The effect they were looking for was incredibly small, a difference in the speed of light of only about 1 part in 100 million. To achieve this sensitivity, Michelson and Morley floated their entire apparatus on a pool of mercury to eliminate vibrations. And they took measurements at different times of day and different seasons to account for Earth's changing direction of motion. Day after day, week after week, they carefully adjusted their mirrors and recorded their measurements. They rotated their apparatus to point in different directions. They repeated their observations as Earth moved to different points in its orbit around the Sun. By all theoretical expectations, they should have detected the ether wind clearly. Instead, they found nothing. No matter which direction they pointed their interferometer, no matter what time of day or what season they conducted their measurements, the speed of light remained exactly the same. There was no ether wind. Light appeared to move at precisely the same speed in all directions, regardless of Earth's motion through space. The Michelson-Morley experiment was, in the words of one physicist, the most famous failed experiment in history. But this failure would prove to be one of the most important non-discoveries in science. The absence of the ether wind suggested something almost unthinkable. Perhaps there was no ether at all. Perhaps light didn't need a medium to travel through. Perhaps it could propagate through completely empty space. But if that were true, it raised even more puzzling questions. How could light maintain a constant speed regardless of the motion of its source or observer? This seemed to violate everything scientists understood about motion and velocity. When you throw a ball from a moving car, the ball's speed relative to the ground is the sum of the car's speed and your throwing speed. Why didn't light behave the same way? The answer to this mystery would require nothing less than a complete revolution in our understanding of space and time themselves. And that revolution would come from a young patent clerk in Switzerland who dared to take the constant speed of light as not a puzzle to be solved, but as a fundamental truth about the universe. Einstein's revolutionary insight. In the spring of 1905, in a modest apartment above the streets of Bern, Switzerland, a young patent clerk named Albert Einstein sat at his desk, surrounded by papers and deep in thought. The Michelson-Morley experiment had been troubling physicists for nearly 20 years. Most were still trying to explain why the aether wind hadn't been detected. Perhaps Earth dragged some aether along with it, or perhaps the instruments had somehow contracted in the direction of motion, masking the effect. But Einstein approached the problem from a completely different angle. Instead of trying to explain away the constant speed of light, he decided to accept it as a fundamental fact about the universe. What if, he wondered, the speed of light in vacuum is truly constant, the same for all observers, regardless of their motion? This seemingly simple assumption led Einstein to one of the most radical insights in the history of science. If the speed of light is constant for all observers, then our everyday notions of space and time must be wrong. Consider this. If you're driving toward a traffic light, the light doesn't appear to be approaching you any faster than if you were standing still. The light from that traffic signal travels at exactly the same speed, whether you're moving toward it or away from it. This means that distance and time themselves must adjust to keep the speed of light constant. Einstein realized that space and time are not separate, absolute entities as Newton had believed. Instead, they are woven together into a single fabric, space-time, that can stretch and contract depending on motion and gravity. When you move very fast, time slows down, and distances contract in precisely the right way to keep the speed of light constant. This insight led to what we now call the special theory of relativity. Among its many startling predictions was one that directly addressed our question about why nothing can go faster than light. As any object with mass approaches the speed of light, its mass effectively becomes infinite, and it would require infinite energy to accelerate it any further. Imagine pushing a heavy box across the floor. At first, it moves easily, but as it speeds up, it becomes harder and harder to push. Now imagine that the faster the box moves, the heavier it becomes. At everyday speeds, this increase is negligible, but as the box approaches the speed of light, its mass grows without bound, making it impossible to push any faster. But Einstein's theory revealed something even more profound about the speed of light. It's not just that light happens to travel at this speed, rather, this speed represents a fundamental property of space-time itself. It's the speed at which causality propagates through the universe, the maximum rate at which information can travel from one point to another. We call it the speed of light, but it would be more accurate to call it the speed of space-time, or the speed of causality. Light happens to travel at this speed because photons have no mass and therefore naturally move at the universe's maximum possible speed. But even if light didn't exist, this speed would still be built into the fabric of reality. Einstein's equation E equals mc squared revealed another profound truth about the speed of light. Mass and energy are interchangeable. The c in this equation is the speed of light, and the fact that it's squared shows just how much energy is locked up in even a small amount of matter. The speed of light isn't just a speed limit, it's the conversion factor between matter and energy, the exchange rate between mass and the potential for motion. As Einstein worked through the implications of his theory in the quiet evenings after his patent office work, he must have marveled at what he had discovered. The speed of light wasn't just a property of light, it was a fundamental constant that governs the structure of reality itself. It determines how space and time behave, how matter and energy relate to each other, and what is causally possible in our universe. The speed of light had revealed itself to be nothing less than the speed of existence itself. The fabric of space-time. To truly understand why nothing can go faster than light, we need to journey deeper into Einstein's vision of space-time. Imagine, if you will, that you could step outside our three-dimensional world and observe it from a higher perspective, like a being who could see not just the surface of a pond, but the entire three-dimensional structure of the water beneath. From this elevated viewpoint, you would see that what we experience as separate moments in time are actually different cross-sections of a larger four-dimensional structure. Past, present, and future all exist simultaneously in this space-time fabric, like different pages in a book that exists all at once, even though we can only read one page at a time. The speed of light in this four-dimensional view is the rate at which we move through time when we're at rest in space. This might seem backwards. We usually think of the speed of light as motion through space, not time. But Einstein's relativity reveals a deeper truth. We are all moving through space-time at exactly the speed of light, always. When you're sitting still, reading these words, you're moving through time at the maximum rate, the speed of light. When you start moving through space, some of your motion through time gets converted into motion through space, so you move through time more slowly. The faster you move through space, the slower you move through time. But your total motion through space-time always equals the speed of light. This is why time dilation occurs. Astronauts on the International Space Station, moving at about 7.66 kilometers per second relative to Earth, age slightly more slowly than people on the ground. They're converting a tiny fraction of their motion through time into motion through space. The effect is minuscule. They age about 0.01 seconds less per year, but it's measurable with atomic clocks and consistent with Einstein's predictions. Light itself represents the extreme case of this trade-off. Photons move through space at maximum speed, which means they don't move through time at all. From a photon's perspective, if such a thing could be said to exist, no time passes during its journey, whether it travels from your reading lamp to this page or from a distant galaxy to your eyes. The photon experiences its entire existence as a single, timeless instant. This four-dimensional view helps us understand why the speed of light represents an absolute limit. It's not that there's some cosmic police force preventing things from going faster. Rather, the speed of light represents the geometry of space-time itself. Asking why nothing can go faster than light is like asking why you can't travel north of the North Pole. It's not a limitation imposed by some external force, but a consequence of the geometry of the space you're moving through. When physicists accelerate particles in the Large Hadron Collider to 99.9999991% the speed of light, they're not fighting against some arbitrary speed limit. They're pushing against the fundamental structure of reality. The energy required to accelerate a particle increases exponentially as it approaches the speed of light, not because the particle becomes more stubborn, but because that energy is being used to warp space-time itself. Consider the mathematics. To double a particle's speed from half the speed of light to the speed of light would require infinite energy. This isn't a practical limitation that clever engineering might someday overcome. It's a mathematical certainty built into the structure of space-time. But there's something beautiful and almost poetic about this limitation. The speed of light serves as a cosmic speed limit that prevents paradoxes and maintains causality. If information could travel faster than light, effects could precede their causes, and the logical structure of the universe would collapse into chaos. Imagine if you could send a signal faster than light to a friend in another galaxy. Due to the relativity of simultaneity, another consequence of Einstein's theory, observers in different reference frames disagree about the order of events. Your faster-than-light message might arrive before you sent it. From the perspective of some observers, this would make it possible to send messages to your own past, creating paradoxes that would undermine the rational order of cause and effect. The speed of light, then, is not just a speed limit. It's the guardian of causality, the protector of logic, the foundation upon which the sensible order of the universe rests.
The quantum dance of light. As the 20th century progressed, physicists discovered that light has yet another layer of mystery. Not only is it both wave and particle, as the double-slit experiment had shown, but it exists in a strange quantum realm where our everyday concepts of reality begin to break down. In the quantum world, light doesn't just travel at the speed of light, it embodies the deepest principles of quantum mechanics. Each photon is a quantum of electromagnetic energy, a discrete packet that carries both wave-like and particle-like properties. When we try to observe it as a particle, it behaves like a particle. When we set up experiments to observe its wave nature, it obligingly behaves like a wave. But quantum mechanics revealed something even stranger about light and the speed limit it represents. In the quantum realm, particles don't have definite positions or velocities. They exist in a superposition of all possible states until the moment of measurement. A photon traveling from a distant star to your eye doesn't take a single path through space. Instead, it takes all possible paths simultaneously,
And these paths interfere with each other just like the waves in Young's double-slit experiment. This quantum behavior applies to all particles, not just photons. When an electron moves from one point to another, it too takes all possible paths, including paths that might seem to require traveling faster than light. But here's where the quantum universe reveals its deep wisdom. These faster-than-light paths cancel each other out through quantum interference. The only path that survives this cancellation is the one that respects the speed of light limit. Richard Feynman, one of the architects of quantum field theory, described this beautifully in his sum-over-paths approach to quantum mechanics. In Feynman's view, a particle considers every conceivable route between 2 points, including zigzag paths, loops, and even paths that go backward in time. But when all of these possibilities are added together using the strange mathematics of quantum interference, only the paths that respect relativistic causality, paths that don't exceed the speed of light, make a significant contribution to reality. The quantum vacuum itself is filled with what physicists call virtual particles, brief fluctuations in the quantum fields that pop into existence and disappear so quickly that they don't violate conservation laws. Some of these virtual particles might seem to propagate faster than light, but they cannot carry information or energy over macroscopic distances. They exist in a liminal realm between existence and non-existence, appearing only in the delicate mathematical formalism of quantum field theory and disappearing before they can violate the fundamental speed limit of causality. This quantum perspective reveals that the speed of light limit is even more fundamental than Einstein's relativity might suggest. It's not just built into the geometry of space-time, it's woven into the very fabric of quantum reality. The universe seems to have developed elaborate mechanisms to ensure that causality is preserved, that effects follow causes, and that the speed of light remains inviolate. Even more remarkably, quantum mechanics has revealed phenomena that seem to violate the speed of light limit, only to preserve it in a deeper sense. Quantum entanglement allows particles to share correlations instantaneously across arbitrary distances. When you measure one particle of an entangled pair, you instantly know something about its partner, even if that partner is on the other side of the universe. But this spooky action at a distance, as Einstein called it, doesn't actually allow faster-than-light communication. The correlations are there, but you cannot use them to send information. The quantum measurements appear random to both observers, and only when they compare their results using conventional, slower-than-light communication do the correlations become apparent. It's as if the universe has a built-in protection mechanism. Quantum mechanics allows instantaneous correlations but prohibits instantaneous communication. The speed of light limit is preserved where it matters most, for the transmission of information and the maintenance of causality.
Modern confirmations and cosmic consequences. In the century since Einstein first proposed his theories, scientists have put the speed of light limit to increasingly rigorous tests. Each experiment has only confirmed what that young patent clerk intuited in 1905. The speed of light in a vacuum is not just very fast, but is the absolute speed limit for anything carrying information or energy through the universe. Consider the most powerful particle accelerators on Earth. At CERN's Large Hadron Collider, protons are accelerated to energies of 6.5 trillion electron volts, reaching speeds of 99.9999991% the speed of light. At these incredible energies, the protons are moving so fast that time dilation becomes extreme. From the proton's perspective, it could circle the Earth's equator in what would feel like 10 nanoseconds, though to us it takes 89 microseconds. Yet despite the enormous energies involved, energies equivalent to a flying mosquito concentrated into a space trillions of times smaller than an atom, these protons never quite reach the speed of light. As their speed approaches this ultimate limit, their apparent mass grows larger and larger, requiring ever more energy to produce ever smaller increases in speed. The mathematics is inexorable.
the final approach to light speed would require infinite energy. But perhaps the most dramatic confirmation of relativity's predictions came on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in space-time itself. These gravitational waves, created by the merger of two black holes 1.3 billion years ago, had been traveling through space at exactly the speed of light, carrying information about one of the most violent events in the universe. The detection confirmed something Einstein had predicted but doubted we would ever be able to observe. Distortions in spacetime propagate at the speed of light. When those two black holes, each about 30 times the mass of our Sun, spiraled into each other in their final cosmic dance, they sent waves through the fabric of reality itself. These waves stretched and compressed space as they passed, but only slightly, changing the length of LIGO's 4-kilometer arms by less than 1/110,000th the width of a proton. The fact that gravitational waves travel at the speed of light reveals something profound. This isn't just the speed of electromagnetic radiation, but the speed of space-time itself. It's the rate at which changes in the geometry of the universe propagate through the cosmos. This discovery has opened new windows into understanding why the speed of light is truly fundamental. In Einstein's theory, mass and energy curve spacetime, and this curvature is what we experience as gravity. When massive objects accelerate, they create ripples in this curvature that spread outward at the speed of light. This speed isn't just a property of light, it's the speed at which cause and effect can propagate through the universe. Astronomers have also found confirmation of light's speed limit in the behavior of the most extreme objects in the universe. When gamma-ray bursts, the most powerful explosions since the Big Bang, occur in distant galaxies, they release more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The gamma rays from these explosions, despite their incredible energies, arrive at Earth traveling at exactly the speed of light, no faster. If photons of different energies traveled at even slightly different speeds, high-energy gamma rays from distant bursts would arrive at noticeably different times than lower-energy photons from the same explosion. The fact that they arrive simultaneously after journeys of billions of years confirms that the speed of light is truly constant across all energies and all distances. Even more remarkably, observations of distant supernovae have allowed scientists to trace the expansion of the universe itself. These cosmic lighthouses, exploding stars whose brightness we can predict, show us that space itself is expanding. But this expansion doesn't violate the speed of light limit. It's the space between objects that's growing, not the objects themselves moving through space faster than light. In fact, there are regions of the universe so distant that their light will never reach us. The expansion of space carries them away faster than their light can travel toward us, creating a cosmic horizon beyond which we can never see. These objects aren't moving through space faster than light. Rather, the space between us and them is expanding so rapidly that light can never bridge the growing gap.
The cosmic symphony of light. As we expand our view from the microscopic quantum realm to the largest scales of the cosmos, we discover that the speed of light orchestrates a grand symphony that has been playing since the birth of the universe itself. In the beginning, according to our current understanding, all the energy that would become matter, stars, galaxies, and ultimately us was compressed into an infinitesimally small point. In the first moments after the Big Bang, the universe was so hot and dense that matter and energy existed in a primordial soup of particles and radiation, all interacting so intensely that light could not travel more than microscopic distances before being absorbed and re-emitted. For the first 380,000 years of the universe's existence, space was opaque to light. Photons would be born from the intense energy, travel briefly, be absorbed by a free electron, and be re-emitted in a random direction. The universe was like a cosmic fog, glowing white-hot but opaque to its own radiance. Then, as the universe expanded and cooled, something remarkable happened. The temperature dropped just enough for electrons to combine with protons and form the first hydrogen atoms.
Suddenly, the cosmic fog cleared. For the first time in the universe's history, light could travel freely through space. This moment, which cosmologists call recombination, marks the birth of transparency in our universe. The light that was released at this moment, light that had been trapped for hundreds of thousands of years, began a journey that continues to this day. We can still detect this ancient light as the cosmic microwave background radiation, a faint glow that fills all of space and provides us with a baby picture of the universe when it was only 380,000 years old. This primordial light has been traveling for nearly 14 billion years, stretched by the expansion of the universe from its original visible wavelengths into microwaves. Every square centimeter of space around you contains about 400 million of these ancient photons, messengers from the universe's infancy, all traveling at the speed of light. But the cosmic symphony of light extends far beyond this ancient background. Stars, those nuclear furnaces that fuse hydrogen into heavier elements, are essentially machines for converting mass into light according to Einstein's E=mc². Deep in their cores, hydrogen nuclei overcome their electrical repulsion and fuse together, releasing the energy that eventually makes its way to the surface and streams out into space at the speed of light. The light from our own sun, generated in fusion reactions at temperatures of 15 million degrees Celsius, takes about 100,000 years to random walk its way from the core to the surface, bouncing from atom to atom in the dense solar interior. But once it reaches the surface and escapes into space, it travels the 150 million kilometers to Earth in just 8 minutes and 20 seconds. This solar light carries with it the energy that powers virtually all life on Earth. Plants capture photons and use their energy to build complex molecules from simple carbon dioxide and water. Animals eat plants or eat other animals that eat plants, ultimately deriving their energy from the nuclear fusion reactions in the sun's core. The fossil fuels we burn were once living organisms that captured ancient sunlight. Even the wind and waves that drive our renewable energy sources are powered by the sun's heating of Earth's atmosphere and oceans. In a very real sense, we are beings made of crystallized starlight. The calcium in our bones, the iron in our blood, the carbon in our DNA, all were forged in the cores of ancient stars and scattered into space when those stars exploded as supernovae. The light from those stellar deaths carried the news of element creation across the galaxy, and eventually the heavy elements condensed into planets, where they became the building blocks of life. Every time you look up at the night sky, you're seeing a temporal mosaic. The light from Proxima Centauri, the nearest star, left its surface 4.24 years ago. The light from the Andromeda Galaxy began its journey 2.5 million years ago, when our earliest human ancestors were just beginning to walk upright on the African savanna. The most distant galaxies visible to our telescopes show us the universe as it was over 13 billion years ago, when the first generations of stars were just beginning to shine. This temporal dimension of vision, the fact that looking out into space is looking back in time, allows us to study the history and evolution of the universe directly. We can watch galaxies forming, stars being born and dying, and the large-scale structure of the cosmos evolving over billions of years. The speed of light doesn't just limit how fast things can move, it provides us with a window into the past, a way of studying cosmic history through direct observation.
The practical magic of light's speed limit. The speed of light might seem like an abstract concept, relevant only to physicists and cosmologists, but it actually governs many aspects of our daily lives in ways both subtle and profound. The technologies we rely on, the communications that connect us, and even the GPS that guides us all depend critically on our precise understanding of light's ultimate speed. Consider your smartphone. When you send a text message to a friend on the other side of the world, that message might travel through fiber optic cables laid across ocean floors, bouncing along as pulses of infrared light at nearly the speed of light through glass fibers thinner than human hair.
The slight delay you sometimes notice in international phone calls isn't due to slow electronics, but to the fundamental fact that light takes time to travel around the globe. About 67 milliseconds to circle the Earth through fiber optic cables. The global positioning system that tells you where you are with meter-level accuracy depends critically on Einstein's theories of relativity and the constancy of the speed of light. GPS satellites orbit Earth at an altitude of about 20,000 kilometers, moving at speeds of roughly 14,000 kilometers an hour. At these speeds, time dilation becomes measurable. The atomic clocks on the satellites run about 7 microseconds per day slow compared to identical clocks on Earth's surface. But there's another effect at work. The satellites are farther from Earth's gravitational field, so they experience slightly less time dilation due to gravity. This gravitational time dilation causes their clocks to run about 45 microseconds per day fast compared to Earth-based clocks. The net effect is that satellite clocks gain about 38 microseconds per day. This might seem negligible, but GPS works by measuring the time it takes radio signals to travel from satellites to your receiver. Since these signals travel at the speed of light, a timing error of 38 microseconds would translate to a position error of about 11 kilometers, making GPS essentially useless for navigation. The system works only because engineers program the satellite clocks to account for relativistic effects, essentially building Einstein's theories into the software that guides your daily travels. The speed of light also governs the flow of information in the modern world. High-frequency trading on stock exchanges is now limited not by computer processing speed, but by the time light takes to travel between trading centers. Traders pay premium prices for the shortest fiber optic routes between financial centers because a few microseconds advantage in receiving market information can translate to millions of dollars in profit. Internet communications face similar constraints. When you video chat with someone on another continent, the delay in your conversation is largely due to the time light takes to travel through underwater cables. Engineers work constantly to minimize these delays, laying cables along Great Circle routes, the shortest paths between continents, to reduce the distance light must travel. The laser interferometer gravitational wave observatories like LIGO represent perhaps the most precise application of our understanding of light's speed. These instruments measure changes in distance smaller than 1/10,000th the width of a proton by precisely timing how long laser light takes to travel down 4-kilometer arms. When a gravitational wave passes through Earth, it slightly changes the length of these arms, and the exquisitely sensitive timing measurements can detect these tiny changes in the travel time of light. Even our understanding of atomic structure and chemistry depends on the speed of light. The fine structure constant, a fundamental number that governs the strength of electromagnetic interactions, is directly related to the speed of light. If light traveled at a different speed, atoms would have different sizes, chemical bonds would have different strengths, and the universe would be a fundamentally different place. In medical imaging, techniques like PET scans rely on the annihilation of matter and antimatter, which produces photons that travel at the speed of light in exactly opposite directions. By precisely timing when these photons arrive at detectors arranged around the patient, doctors can reconstruct three-dimensional images of metabolic activity inside the body. Laser surgery uses the speed and precision of light to perform delicate operations. Because light travels so fast and can be focused so precisely, laser pulses can deliver energy to exactly the right location in a patient's eye to reshape the cornea and correct vision, or to precisely ablate cancerous tissue without damaging surrounding healthy cells. Even the screens you're reading this on rely on the speed of light. LCD displays work by controlling how polarized light passes through liquid crystal materials, while OLED displays generate light through electroluminescence, the conversion of electrical energy directly into photons that travel at the speed of light from the screen to your eyes.
The edge of the impossible. As our understanding of the speed of light deepens, physicists continue to probe the boundaries of what's possible within this ultimate cosmic speed limit. They've discovered phenomena that seem to challenge our intuitions while ultimately confirming the fundamental nature of light's speed as the universe's ultimate boundary. In quantum mechanics, we've discovered that information can sometimes appear to travel faster than light, but in ways that cannot be used for actual communication. Quantum tunneling allows particles to pass through barriers that should be impenetrable, according to classical physics. When a particle tunnels through such a barrier, it can appear on the other side in less time than it would take light to travel the same distance through empty space. But this apparent faster-than-light travel comes with a catch. The process is probabilistic and cannot be used to send information. You cannot control when or if a particular particle will tunnel through a barrier, so you cannot use quantum tunneling to send a message faster than light. The universe preserves causality even while allowing these strange quantum phenomena. Similar principles apply to the Casimir effect, where quantum fluctuations in empty space create measurable forces between closely spaced metal plates. Virtual particles appear to pop into existence and disappear so quickly that they don't violate conservation laws, but their brief existence creates real, measurable effects. Some of these virtual particles might seem to travel faster than light, but they exist in the liminal space between reality and possibility, never quite becoming real enough to carry information. Researchers have also discovered ways to manipulate the speed of light itself and specially prepared materials. In 1999, physicist Lin Hao and her team managed to slow light down to just 17 meters per second, slower than a bicycle, by passing it through a Bose-Einstein condensate of ultra-cold sodium atoms. Later, they managed to stop light completely, store it, and then release it unchanged. These experiments don't violate the fundamental speed limit because the c in Einstein's equations refers specifically to the speed of light in vacuum. In materials, light interacts with atoms and can be slowed down considerably. But the underlying speed limit, the speed at which causality propagates through spacetime, remains unchanged. Other researchers have created materials with negative refractive indices where light appears to bend backward and travel in unexpected directions. Still others have achieved superluminal group velocities where the peak of a light pulse appears to travel faster than the speed of light in vacuum. But in all these cases, careful analysis shows that no information actually travels faster than light and causality is preserved. These experiments illuminate an important distinction. There are many different ways to define the speed of light, and while some of these speeds can be manipulated or can exceed the vacuum speed of light, the fundamental speed limit, the speed at which information and causality propagate, remains inviolate. Perhaps the most intriguing recent developments involve the study of black holes and the nature of space-time itself. At the event horizon of a black hole, space and time become so severely warped that time effectively stops from the perspective of a distant observer. Light emitted just at the event horizon would take infinite time to escape to the outside universe, although from the perspective of someone falling through the horizon, everything would seem normal. They would cross the horizon at the speed of light relative to local space-time. These extreme environments provide natural laboratories for testing our understanding of the speed of light under the most extreme conditions in the universe. So far, every observation confirms that the speed of light remains constant even in the most warped spacetime, even at the edge of black holes where gravity is strong enough to bend light into closed orbits. Theoretical physicists continue to explore whether there might be any exceptions to the speed of light limit. Some theories suggest that in the earliest moments after the Big Bang, space itself expanded faster than light, but this doesn't violate relativity because it's the expansion of space itself, not the motion of objects through space. Other theories propose the existence of hypothetical particles called tachyons that would always travel faster than light, but such particles would have imaginary mass and would violate causality in ways that seem to make them impossible in our universe.
String theory and other quantum gravity theories suggest that at the smallest scales, the Planck length, about 10 to the minus 35 meters, space-time itself might become grainy or foamy, potentially modifying our understanding of the speed of light. But even these speculative theories preserve the essential role of the speed of light as a fundamental constant that governs the structure of reality.
The philosophy of cosmic speed limits. As we near the end of our journey through the mystery of light speed, it's worth pausing to consider what this ultimate speed limit tells us about the nature of reality itself. The speed of light is more than just a physical constant. It's a window into the deep principles that govern existence. Consider what the universe would be like without this speed limit. If information could travel instantaneously across any distance, cause and effect would lose their meaning. You could influence events in the past, creating paradoxes that would make rational thought impossible. The ordered sequence of cause and effect that allows science, logic, and even consciousness to exist would collapse into chaos. The speed of light serves as a cosmic traffic controller, ensuring that events unfold in a logical sequence. It creates what physicists call light cones, regions of spacetime that can causally influence each other. Events outside your light cone cannot affect you now, and you cannot affect them until light has had time to travel between your locations. This might seem like a limitation, but it's actually what makes complex structures possible in the universe. Galaxies can exist as distinct entities because information takes time to travel between their distant parts. Stars can maintain their structure because changes in their cores take time to propagate to their surfaces. Life can evolve and develop because biological processes have time to unfold without being instantly disrupted by every distant event in the universe. The finite speed of light also gives the universe a kind of privacy. What happens in distant galaxies cannot instantly affect us, giving local processes the stability they need to develop complexity. It's as if each region of space has its own neighborhood, insulated from instant influence by distant events. There's something almost ethical about this speed limit. It prevents any single event from instantly dominating the entire universe. It ensures that influence must be earned through the patient process of propagation across space and time. It makes the universe democratic in a sense. No location is privileged to instantly control all others. The speed of light also gives meaning to the concept of now. Without a finite speed for information, there would be no meaningful distinction between different moments in time. Everything would be instantaneously connected to everything else. The finite speed of light creates a structure to time, making it possible for there to be a sequence of moments, a flow from past to future. From a philosophical perspective, the speed of light embodies several profound principles. It represents the universe's commitment to consistency. The same rules apply everywhere and at all times. It demonstrates the universe's resistance to paradox. The speed limit prevents logical contradictions from arising. And it reveals the universe's tendency toward complexity. By preventing instant global influence, it allows local structures to develop and evolve. Some philosophers have noted that the speed of light creates a kind of cosmic loneliness. The farther we look into space, the further we're looking into the past. There is no way to see the universe as it is now on large scales. We can only see how it was. This temporal isolation means that each conscious observer exists in a kind of bubble, surrounded by images from the past, forever cut off from immediate knowledge of the present state of distant places. But this isolation also creates possibility. Because information takes time to travel, the future remains open. The speed of light ensures that the universe has room for surprise, for creativity, for the emergence of new possibilities that couldn't be instantly predicted or controlled by existing conditions. The constancy of the speed of light also speaks to something aesthetically beautiful about the universe. Despite all the complexity and chaos we observe, there are underlying simplicities.
fundamental constants that remain the same everywhere and always. The speed of light is one of these deep simplicities, a number that emerges from the basic structure of space-time itself. In many spiritual traditions, light has been associated with truth, consciousness, and the divine. It's remarkable that modern physics has revealed light to be associated with such fundamental aspects of reality: causality, information, the structure of space and time. The speed of light isn't just a property of electromagnetic radiation. It's the speed at which reality itself unfolds. Future horizons and eternal constants. As we look toward the future, both near and unimaginably distant, the speed of light will continue to shape the possibilities and limitations of existence in our universe. No matter how advanced our technology becomes, no matter how deeply we understand the quantum realm or how far we venture into space, we will always be operating within the framework established by this fundamental constant. In the coming decades, our growing mastery of quantum mechanics will likely lead to new technologies that push closer to the limits imposed by the speed of light. Quantum computers, which harness the strange properties of quantum superposition and entanglement, will allow us to process certain types of information exponentially faster than classical computers. But even quantum computers cannot violate the speed of light. They cannot be used to send information faster than light, and their quantum operations still unfold at rates limited by the fundamental constants of physics. Space exploration will always be constrained by the finite speed of light. As we send probes to other star systems, communication delays will stretch from minutes to hours to years. A probe visiting Proxima Centauri, our nearest stellar neighbor, would experience communication delays of over 4 years each way. Commands sent from Earth would be responses to conditions that existed 4 years earlier, and reports from the probe would describe situations from 4 years in the past. This creates a fundamental challenge for interstellar exploration. Autonomous decision-making becomes essential. Spacecraft venturing to other stars must be capable of independent thought and action because real-time control from Earth becomes impossible across interstellar distances. The speed of light forces us to create truly intelligent machines, artificial minds capable of exploring the universe on our behalf while we wait years for news of their discoveries. Even if we develop technologies that seem to circumvent the speed of light limit, such as hypothetical concepts like wormholes or warp drives, these would still operate within the framework of Einstein's relativity. Wormholes, if they could exist and be stabilized, would be shortcuts through space-time rather than violations of the speed limit. Warp drives, as conceived by physicist Miguel Alcubierre, would work by contracting space in front of a spacecraft and expanding it behind, allowing the ship to effectively travel faster than light without locally exceeding the speed limit. But these exotic concepts require forms of matter and energy that may not exist in our universe. Exotic matter with negative energy density or energy requirements equivalent to the mass of entire stars. The speed of light limit may prove to be truly absolute even for the most advanced civilizations imaginable. As we consider the far future of the universe itself, the speed of light will continue to play a crucial role in cosmic evolution. The accelerating expansion of space means that distant galaxies are receding from us at ever-increasing rates. Eventually, galaxies beyond our local group will be carried away so fast by the expansion of space that their light will never reach us. The observable universe will shrink, not because light is slowing down, but because space itself is expanding faster than light can cross it. In the unimaginably distant future, when the last stars have burned out and the universe has grown cold and dark, the speed of light will still govern the final processes of cosmic evolution. Protons, if they decay as some theories predict, will disappear at rates governed by quantum mechanical processes that respect the speed of light limit. Even the evaporation of black holes through Hawking radiation proceeds at rates determined by the fundamental constants of physics. Throughout all these eons, the speed of light will remain constant. 299,792,458 meters per second in vacuum, unchanged since the universe began. It will still be the speed at which causality propagates, the conversion factor between mass and energy, the fabric from which spacetime is woven. This constancy across all time and space speaks to something profound about the nature of reality. In a universe of constant change, where stars are born and die, galaxies collide and merge, and even space itself expands and evolves, the speed of light remains as an eternal constant, a fixed reference point in the flowing river of cosmic change. For conscious beings like ourselves, living brief lives in this vast cosmic story, the speed of light serves as both a limitation and a liberation. It limits how quickly we can explore the universe, how fast we can communicate across distances, how rapidly information can flow. But it also creates the stable framework within which consciousness, complexity, and beauty can emerge. The speed of light ensures that we live in a universe where effects follow causes, where the future remains open to possibility, where local processes can develop complexity without being instantly overwhelmed by distant influences. It creates a cosmos where intelligence can evolve, where life can flourish, where beings can contemplate the mysteries of existence itself. The light that connects all things. And so we come to the end of our journey through the mystery of the speed of light, though in truth, every ending in science is just the beginning of deeper questions, more profound mysteries, greater wonders to explore. We began with the simple experience of light touching your face, and we've discovered that this everyday phenomenon connects you to the deepest structures of reality. The light that illuminates these words as you read them is traveling at a speed that governs the flow of time itself, the conversion of matter to energy, the propagation of cause and effect throughout the universe. That speed, 299,792,458 meters per second, is not just fast. It is the speed at which reality unfolds, the rate at which the possible becomes actual, the velocity of existence itself. It is woven into the fabric of space-time, embedded in the mathematics of quantum mechanics, and encoded in the structure of atoms, stars, and galaxies. Every photon that has ever reached your eyes has been traveling at exactly this speed, whether it was born in the nuclear furnace at the center of our sun, in the LED of your reading lamp, or in a distant galaxy billions of years ago. These photons carry with them not just images of the world around you, but information about the fundamental nature of the universe itself. The constancy of the speed of light tells us that we live in a rational universe, one governed by consistent laws that apply everywhere and at all times. It assures us that the same principles that govern the behavior of light in our laboratories also govern the light from the most distant galaxies, making astronomical observations meaningful and scientific predictions possible. The finite nature of light's speed tells us that we live in a universe with structure, where events unfold in logical sequence, where causes precede effects, where the future remains open to possibility. It creates the framework within which complexity can emerge, consciousness can evolve, and beings like ourselves can exist to contemplate these mysteries. The speed of light is the universe's way of maintaining both connection and separation. It connects us to distant stars and ancient events, carrying information across vast gulfs of space and time. Yet it also creates a kind of cosmic privacy, ensuring that each region of space has the isolation it needs to develop its own unique character and complexity. As you go about your daily life, remember that you are constantly interacting with one of the most fundamental constants in the universe. Every time you see anything, you are experiencing the speed of light. Every time you use GPS, send a text message, or watch a sunset, you are relying on our understanding of this cosmic speed limit. The light that touches your face in the morning carries with it the history of the cosmos, photons that may have journeyed for millions or billions of years to reach you, messengers from the deep past carrying news of distant worlds and ancient events. The light that guides you through your day connects you to the network of fiber optic cables that span the globe, to the satellites orbiting overhead, to the fundamental processes that power all modern technology. And perhaps most remarkably, the speed of light ensures that there is still mystery in the universe. The finite time it takes light to travel means that we can never see the universe as it is now on large scales, only as it was. There are regions of space so distant that their light has not yet had time to reach us since the universe began. There are events happening now in distant galaxies that we will not learn about for millions or billions of years. This creates a universe full of surprises, a cosmos that retains the capacity to amaze and wonder us no matter how much we learn. The speed of light is more than a number, more than a physical constant, more than a limitation on how fast things can go. It is the fundamental rhythm of existence, the metronome that keeps time for the cosmic symphony, the thread that weaves together space and time into the fabric of reality.
And in the end, perhaps that's the most beautiful thing about the speed of light. It shows us that we live in a universe that is both vast beyond imagination and intimate in its connections, both ancient beyond measure and immediate in its presence, both governed by immutable laws and rich with endless possibilities. The light that began our story by touching your face is still there, still traveling at its eternal speed, still carrying with it the deep mysteries and profound beauties of the cosmos. In understanding why nothing can go faster than light, we haven't just learned about a speed limit. We've discovered one of the fundamental principles that makes existence itself possible. So the next time light touches your face, whether it's sunlight streaming through a window, starlight on a clear night, or the glow from your reading lamp, remember that you are experiencing one of the universe's most profound truths. That reality has a rhythm, existence has a pace, and that pace is exactly 299,792,458 meters per second. Nothing can go faster than light, not because of some arbitrary cosmic rule, but because that speed is woven into the very fabric of what it means to exist. It is the speed of time, the velocity of causality, the rate at which the universe writes the story of its own existence, a story in which we are not just observers, but participants, connected to every star, every galaxy, every moment in cosmic history by the endless stream of light that flows through the universe at its own perfect, unchangeable, eternal speed. The first flicker of light. Imagine the universe before there were eyes to see it. It was silent. Not the quiet you know from midnight in your room, but a deeper stillness. A silence untouched by sound, for there was no air yet to carry it. The darkness stretched in every direction, not the cozy darkness of closed eyelids, but the raw, infinite darkness of a cosmos without stars. And then a flicker. It was not just brightness, it was light, the very first whisper of it, spilling into the void like the first breath after a long sleep. It carried with it something that would, much later, become the heartbeat of physics. A speed. A speed so perfect, so absolute, that it would become the very foundation upon which space and time themselves were built. That speed would one day be called 299,792,458
458 meters per second.
The first puzzling clues. By the 17th century, the age of curiosity had arrived in Europe. The Renaissance had rekindled a hunger for knowledge. Lenses and telescopes had revealed moons around Jupiter, craters on our own moon, and the Milky Way's countless stars. And somewhere in this whirl of discovery, a young Italian named Galileo Galilei decided to test whether light had a measurable speed. He and a friend each carried a lantern, covered so its light could be hidden at will. They stood on distant hilltops, far enough apart that their voices couldn't carry. Galileo would uncover his lantern, and the moment his friend saw the light, he would uncover his own, sending a signal back. If there was any delay, Galileo could measure it. But every time, the light seemed to return instantly. His conclusion? If light had a speed, it was far too fast for his crude instruments to measure. He wasn't wrong, he was simply asking a question with no earthly answer yet. Ole Romer and the moons of Jupiter. A few decades later, in 1676, a Danish astronomer named Ole Romer found himself staring at Jupiter through a telescope. But he wasn't watching the planet itself. He was watching its moon, Io, slipping in and out of Jupiter's shadow. Romer noticed something strange. The timing of Io's eclipses wasn't constant. Sometimes Io seemed to emerge a little early, sometimes a little late. Most astronomers blamed errors in observation. But Romer had a wilder thought. What if light doesn't reach us instantly? What if the delays were caused by Earth moving farther or closer to Jupiter as it orbited the Sun? His calculations led to a radical conclusion. Light took time to travel, and its speed was finite. Though his exact number wasn't perfect, he became the first human in history to put a measurement, a real, physical limit on the speed of light. The universe's invisible speed limit. Over centuries, experiments refined that number. From Hippolyte Fizeau's toothed wheel apparatus in 1849 to Albert Michelson's rotating mirrors in the 1870s, the precision grew sharper and sharper. Eventually, in 1983, the speed of light became so well known, so exact, that scientists fixed it as a constant of nature, not something to be measured anymore, but something to define our units of distance and time. And here lies the most humbling truth. Light is not just fast, it is the fastest. Nothing, no object, no signal, no dream can go faster. Why? It's tempting to imagine the universe as a vast racetrack, with light in the lead and everything else simply unable to catch up. But the truth is more profound. According to Albert Einstein's special theory of relativity, the speed of light isn't just a property of light, it's a property of the universe itself. Space and time are woven together in a cosmic fabric, and the speed of light is the thread that determines how that fabric bends and stretches. To go faster than light isn't just breaking a speed limit, it's breaking reality's loom. The closer you get. Imagine you are in a spaceship. You push your engines harder and harder. At first, your speed climbs easily, but as you near the speed of light, strange things happen. Time slows for you, not in the poetic sense, but literally. Clocks aboard your ship tick more slowly compared to those back on Earth. Your mass increases, not because you're gathering material, but because energy itself begins to weigh upon you. The universe resists your approach. It whispers, "You may come close, but you will never overtake light." A cosmic law written in light. We live in a strange paradox. Light is everywhere, touching your skin, warming your face, glinting in the eyes of those you love. Yet it is also untouchable. It is both the simplest thing to see and the most impossible thing to outrun. And so, when we look at the night sky, we are not just looking into space, we are looking into the past, because light, though imaginably fast, still takes time to arrive. The sunlight falling on you left the sun 8 minutes ago. The light from Alpha Centauri began its journey over 4 years ago, and the faint glow of distant galaxies began before Earth even existed. Light connects us to history. It stitches the present to the past, one photon at a time. The first flicker forever. That first flicker, born in the early universe, still moves, unstoppable, unchanged. It carries with it the same message it has always had. There is a speed, a perfect speed that shapes reality itself. And within that speed lies the quiet law that nothing, no matter how determined, can ever go faster.
The story of light's speed is not just a story about science. It is a story about limits and the beauty within them. For perhaps it is because nothing can go faster than light that the universe has time to unfold its wonders and for us to see them. Chasing the impossible. The yearning to outrun light is older than the word physics. It began in myth, in tales of chariots blazing across the sky. In the Rig Veda of ancient India, the sun is driven by the swift horse of Surya, crossing the heavens each day. In ancient Greece, the god Helios rides his golden chariot from east to west. These were not just stories of beauty, they were stories of speed. By the 19th century, the human race had begun its own chariot rides, steam trains screaming across continents, ships cutting through oceans, telegraphs sending messages in an instant. Each invention made the world smaller, each one faster than the last. The unspoken question returned: if we can make machines that outpace horses, wind, and sound, could we one day outrun light? Science fiction gave the most daring answers. Writers imagined warp drives, hyperspace jumps, wormholes, and tachyons, particles that travel faster than light. Jules Verne and later H.G. Wells told of cosmic voyages unconstrained by physics. On the page, light's speed limit was just another obstacle for heroes to overcome. But reality was already whispering a quieter, more stubborn truth. Nature does not bend easily. Einstein's curtain. In 1905, a young patent clerk named Albert Einstein published a paper that would become one of the most famous in history. It was not full of grand language or cosmic poetry, just precise mathematics, but in its numbers was a revolution. Einstein said, the speed of light is not just fast, it is unchangeable. It is the same for everyone, everywhere, no matter how they move. This was not a human preference. It was woven into the geometry of the universe itself. It meant that chasing light was like chasing the horizon. You could run, but the finish line would always stay ahead. The cost of the chase. Einstein's equations revealed something strange. If you try to move faster, your time slows relative to the outside world. If you keep pushing, your mass increases, and the energy needed to accelerate grows without end. Reaching the speed of light would require infinite energy, and infinity is not available in nature's pantry. The cosmic race we cannot win. Still, humans are restless creatures. We build particle accelerators to fling protons to 99.99999% of light speed. We watch them circle giant rings underground, colliding with unimaginable force. But even these champions of speed, the fastest particles we can create, never touch light's pace. They approach it, closer and closer, but never cross the final fraction of a percent.
It's as if the universe lets us glimpse the finish line, but not step over it. Light as the messenger. Why this limit? Because the speed of light is not just about light. It is about information. Nothing, no signal, no sound, no particle can carry information faster than light. And information is the skeleton of reality itself. If something could outrun light, cause and effect could flip. The future could happen before the past. Paradoxes would bloom like weeds. The timeline of the universe would shatter. So nature locks the gate.
Time, space, and the fabric of the universe. To understand why nothing can go faster than light, we must stop thinking of speed as just a number. Einstein's special theory of relativity tells us that space and time are not separate. They are threads of the same fabric, space-time, and light's speed is the way that fabric is woven. The cosmic loom. Imagine space-time as an endless sheet. Every object, every planet, every galaxy is a weight upon it, bending it into gentle curves. Light moves along these curves, always at the same pace, like a ripple traveling across the surface of a pond. If you could move faster than light, you would no longer be moving along the fabric, you would be tearing through it. And space-time has no rules for such tearing. It would be like trying to write a story with letters that haven't been invented yet. The twin paradox. Relativity brings with it one of the strangest predictions. If you travel close to the speed of light and return, you will have aged less than those who stayed behind. This is no science fiction. It has been measured with atomic clocks on airplanes and satellites. Time itself bends in the presence of speed, and the closer you get to light's speed, the more it bends. Mass as resistance. Another barrier emerges: mass. At ordinary speeds, mass is steady, but as your velocity grows, your mass effectively increases. It takes more and more energy to accelerate you further. At light speed, your mass would be infinite, and infinite mass requires infinite energy, an impossibility in our finite universe. Light's special privileges. Light itself avoids this problem by being massless. A photon, a single particle of light, has no rest mass. That is why it can travel at this ultimate speed without the impossible burden of infinite energy. But this also means photons cannot slow down. They are born at light speed and will move at light speed until they are absorbed. In a way, a photon's entire life is spent in motion, without ever knowing what it means to be at rest. A universe in delay. The universe is huge. Even at light speed, messages from one side to the other take billions of years. This is why when we look at distant galaxies, we see them as they were long ago. Some of the light hitting your eyes tonight left its source before Earth existed. When you gaze upward, you are looking into history, not a picture of now, but a shimmering mosaic of the past. The event horizon. At the edge of a black hole lies the ultimate test of light's speed. The event horizon, here, the pull of gravity is so intense that even light cannot escape. Not because it has slowed, but because space-time itself is curved inward faster than light can climb outward. Beyond this horizon, events are sealed away from the rest of the universe forever. The dreamers who defied the limit. Despite knowing the barrier, humanity dreams of crossing it. Writers invent starships that warp space-time, creating shortcuts. Theoretical physicists speculate about wormholes, tunnels through the fabric of reality. Alcubierre's bubble. In 1994, physicist Miguel Alcubierre proposed a mathematical model for a warp drive. Instead of moving through space faster than light, the idea was to compress space ahead of the ship and expand it behind it. The ship itself would sit still inside a bubble of space-time,
carried along like a leaf on a moving river. It didn't violate relativity, in theory, but in practice it would require exotic matter with negative energy, something not yet found in nature. The tachyon temptation. Physicists have also played with the idea of tachyons, hypothetical particles that always move faster than light. If they exist, they would break the normal order of cause and effect. But so far, no experiment has found them, and many suspect they are a mathematical curiosity, not a real inhabitant of the universe. Why the limit matters. Without a cosmic speed limit, the universe might be chaos. If messages could travel instantly, effects could precede causes. The future could influence the past. Logical contradictions, like receiving a warning from yourself before the danger occurred, could arise. The safety of slowness. Light's limit ensures order. It gives the cosmos a structure where events have a consistent sequence, where cause leads to effect. It gives galaxies time to form, stars time to shine, and life time to evolve. The poetry of boundaries. Limits are not just walls, they are shapes. A violin string's limit is what lets it sing. The horizon's limit is what makes sunsets beautiful. The speed of light is the universe's way of setting a rhythm to the cosmic dance. Living at the speed of light. Imagine for a moment being a photon. From its perspective, no time passes between its birth and its death. A photon emitted in the heart of a star and absorbed by your eye experiences both events at once. This strange truth, that at light speed time stands still, is one of the most profound in physics. A universe in frames. Every speed gives a different frame of reference. At our slow human speeds, we agree on lengths, times, and sequences. But at relativistic speeds, those agreements dissolve. The universe is not the same for everyone. It depends on how you move through it. The far future of speed. What will speed mean to civilizations millions of years from now? Perhaps we will never outrun light, but we might learn to bend the paths it takes. We might harness quantum entanglement for communication, or master the folding of space-time. But the speed of light itself will remain unbroken, as it has for 13.8 billion years. Signals from the end. Someday, distant galaxies will slip beyond our observable horizon. Their light will never reach us again. The universe's expansion will carry them away faster than their light can close the gap. In the far future, our cosmic neighborhood will be all we can see. The quiet law. The speed of light is more than a number. It is a promise from the universe, a promise that space and time have an order, that events are stitched together in a way that makes sense. We may never break it, but perhaps that is not the point. The point is that this limit gives meaning to distance, to time, to the act of looking up at the stars and knowing they are both near enough to see and far enough to make us dream. Closing reflection. The first flicker of light still moves, unchanged across the dark. It does not slow, does not tire, does not break its own law. In that constant motion lies the story of the universe, and the quiet truth that some limits are not prisons, but the very shape of freedom. Einstein's Year of Miracles, 1905. It was the year 1905, in the city of Bern, Switzerland. A young man worked in a small, modest room at the Swiss Patent Office. His desk was cluttered, papers stacked in uneven towers, an old inkwell resting beside a half-burnt candle, and the faint smell of pipe smoke drifting in from the hallway. The man's name was Albert Einstein. He was not yet the Einstein the world knows, not the icon, not the genius framed in black and white photographs with wild hair and deep, knowing eyes. He was simply a 26-year-old clerk with a restless mind. Each day he reviewed patent applications, inventions for clocks, engines, and mechanical devices. But between those papers, his thoughts wandered far beyond Switzerland. He dreamed of trains moving at unimaginable speeds, of beams of light stretching into infinity, of what the world might look like if you could ride a photon across the universe. In that single year, his Annus Mirabilis, or Year of Miracles, Einstein published 4 groundbreaking papers that would change physics forever. One of them shattered centuries of belief about space and time. The seed of relativity. Einstein proposed something astonishing. The speed of light is the same for everyone, no matter how fast they are moving. It didn't matter if you were on a moving train or standing still on the platform. Light would reach you at the same speed. To make that possible, space and time themselves would have to bend and stretch. Time could slow down. Distances could shrink. Reality was not a rigid stage. It was a flexible fabric. And in that flexible fabric lay the reason nothing could go faster than light. Einstein wasn't working in a grand university lab when he realized this. He had no expensive equipment, only his mind. And in the quiet of that patent office, he redefined the limits of the universe. The nature of time and why it's not absolute.
Before Einstein, time was thought of as a steady river. It flowed the same for everyone, everywhere. You could set your clock in Paris and another in New York, and they would tick in unison forever, as long as they were precise enough. But relativity revealed that time is not a universal drumbeat. It is personal. It depends on where you are and how you move. Time's secret flexibility. Imagine 2 identical twins. One stays on Earth. The other boards a spaceship and travels close to the speed of light for several years. When the traveler returns, she has aged less than her sister. The faster she moved, the slower her time flowed. This is not a thought experiment anymore. We've tested it. Clocks flown on airplanes run ever so slightly slower than clocks on the ground. GPS satellites orbiting Earth experience both slower time due to their speed and faster time due to being farther from Earth's gravity. Engineers must correct for both, or GPS would drift kilometers off course. Time is not a background. It is part of the stage built by light's speed. The messenger of the universe. Close your eyes for a moment and imagine the very first time a human being looked up at the night sky and truly saw the stars, not as points of light, but as messengers. We do not see them as they are now. We see them as they once were. That is the strange magic of light. It is always telling us a story from the past. The nearest star to us, apart from the Sun, is Proxima Centauri. Its light takes more than 4 years to reach our eyes. When you gaze at it tonight, you are seeing it as it was over 4 years ago. If at this very moment something remarkable were to happen there, a flare, a change, a cataclysm, we would not know until 4 years from now. In that sense, the universe is like an ancient postman, delivering messages with an unchanging speed, unable to rush, unable to delay. The speed of light is not merely a number. It is a law of storytelling. It sets the pace of the universe's narrative. Every photon that touches your skin carries the history of where it has been,
from the nuclear furnaces of a star, through the void, across unimaginable distances, until it meets you. Scientists have spent centuries trying to measure this speed precisely, but nature already knew its value long before we did. 299,792,458 meters per second, an exact number, a sacred rhythm written into the fabric of reality itself. The first attempts to chase the light. Centuries ago, before we had telescopes that could split a star's light into rainbows, before we had satellites whispering to each other in orbit, we had questions. Could light travel instantaneously, or did it take time to move from place to place? The ancient Greeks debated it. Some believed light was instantaneous. Others thought it traveled at a finite, though unknown, speed. It was a puzzle that lingered for almost 2,000 years. Then, in the 17th century, a Danish astronomer named Ole Romer noticed something strange while studying Jupiter's moons. One moon, Io, seemed to vanish and reappear at slightly different times depending on whether Earth was moving toward or away from Jupiter in its orbit. Romer realized he was seeing the effect of light's finite speed. It took longer for Io's signal to reach us when Earth was moving away from Jupiter. His calculations weren't perfect by modern standards, but they were revolutionary. For the first time, humanity had proof light has a speed, and it is not infinite. That single realization set us on the path to understanding the universe's ultimate speed limit.
The cosmic speed limit revealed. The 19th and early 20th centuries brought us closer and closer to the truth. The work of James Clerk Maxwell united electricity and magnetism into one elegant theory, predicting that light itself was an electromagnetic wave, moving at a fixed speed through the vacuum. Then came Albert Einstein. In 1905, with his special theory of relativity, he made a bold declaration. The speed of light is the same for everyone, no matter how fast you are moving. This was not just a detail of physics, it was a revolution in our understanding of reality. Imagine two ships passing each other in the darkness, both turning on their spotlights. In the old Newtonian view, if you were moving toward a beam of light, you might expect to see it approach you faster than if you were moving away. Einstein said no. The beam's speed is always the same. It is space and time themselves that will bend, stretch, and warp to make sure that truth holds. This single idea reshaped everything. It told us there was no way to outrun light. No clever trick, no hidden path, no shortcut. The cosmic speed limit is not a suggestion. It is the architecture of reality. The lantern in the abyss. Far beyond the last warm breath of a star, beyond the outermost fringes of its planets and the thin whispers of cosmic dust, there lies a realm so dark it feels almost like a forgotten thought in the universe's mind. This is the abyss, not the dramatic, stormy darkness of a tempest, but the cold, endless black that has been undisturbed for billions of years. In this abyss, there is only one kind of messenger fast enough to cross it in any reasonable time: light. And yet even light, with all its swiftness, takes ages to carry a story across the void. Imagine for a moment you hold a lantern here. The glow is warm in your hand. You turn slowly, and that light spills into the darkness like a spill of gold ink into an infinite black ocean. At first, it seems fast, racing away. But then you remember, even at 299,792 kilometers per second,
It will take over 4 years for this light to simply reach the nearest star. And that is the nearest one. Out here, you feel time stretching in strange ways. The human mind measures seconds, minutes, hours, but the lantern's glow is working on a cosmic clock, one where journeys take millennia. In this slow, endless voyage, you begin to realize light is the fastest thing we know, and yet the universe is so staggeringly vast that even light feels patient. It is a lantern in the abyss, crossing eternity, 1 second at a time. The cosmic river. Think of the universe as a vast river, not of water, but of space-time itself. When Albert Einstein looked at the equations of his theory of relativity, he saw that space and time were not separate things. They were intertwined, like the currents and eddies of a great river. Massive objects, like stars and planets, dip into this river, shaping the flow around them. This is why planets orbit stars, why moons orbit planets. They are not being pulled by an invisible force. They are following the curved flow of the river beneath them. Now, in this river, there is a speed limit. Just as in a real river you cannot row faster than the current allows, in the river of space-time, nothing can move faster than light. Why? Because light itself is the way we measure the flow of the river. You see, light is not just a traveler in space-time. It is part of the very fabric of it. To go faster than light would be to tear through the river itself, breaking the current that defines reality. Here's something humbling. If you are in this cosmic river, you are already moving at the speed of light in one sense. Einstein explained that all objects, even stationary ones, are constantly moving through space-time at the speed of light. If you are not moving through space, you are moving through time. If you move faster through space, you move slower through time.
The cosmic river flows on, indifferent, eternal. And in its currents, light is the swiftest ripple we will ever know. The wall of infinity. There's a strange thing about trying to go faster than light. It's not like trying to run faster than your friend or drive faster than another car. It's not even like trying to outrun sound. It's more like trying to reach the edge of infinity. You see, as you push an object faster and faster, its energy, and therefore its mass, begins to increase. This isn't just poetic language. In Einstein's equation, E equals mc squared, the energy and mass are two sides of the same coin. Push an object hard enough, and the energy you give it starts to turn into mass. And the closer you get to the speed of light, the more extreme this becomes. At 99% of light speed, you are already enormously heavier than you were at rest, not in terms of eating too many desserts, but in terms of relativistic mass. The energy needed to keep accelerating you skyrockets. At 99.99999%, you would need near infinite energy just to push a little faster. And at 100%, the speed of light itself, the math breaks. The energy required becomes literally infinite. The wall is unbreakable, not because we don't have the right machines, but because the very laws of physics refuse to allow it. It's as if the universe itself whispers, "This is the boundary, here and no further." When the stars are memories. There's a quiet tragedy in the speed of light. It means that every time you look at the stars, you are looking into the past. The sunlight,
warming your face, left the sun 8 minutes ago. The light from Sirius took 8.5 years to reach you. The glow of the Andromeda Galaxy left there over 2 million years ago, when early humans had not yet spoken their first words. The universe you see tonight is not the universe that exists tonight. It is a sky made of memories. And the faster you try to chase those stars, the more impossible it becomes. The light has already left. You cannot catch it. You can only wait for more to arrive. Little parcels of history drifting endlessly through space. And perhaps there's a strange comfort in that. Even when a star dies, its light continues on, crossing the abyss. For hundreds, thousands, even millions of years, it will still shine in some faraway sky. Light is both fragile and immortal. It tells the universe's oldest stories, one photon at a time. The secret in the equation. Let's return to the most famous equation in physics. E equals mc squared. It's printed on t-shirts, posters, mugs, but it's more than a piece of science pop culture. It's a cosmic secret, hiding in plain sight. What Einstein revealed was that energy and mass are not separate things. They are simply different forms of the same essence. The c in the equation, the speed of light, is the bridge between them. It's not there because light is special in a random way. It's there because light defines the structure of reality itself.
Whenever you see that C, know that it's not just a number. It is the cosmic conversion rate between the stuff of the universe, mass, and the fire of the universe, energy. And because C is so enormous, 300 million meters per second, even a tiny bit of mass contains an astonishing amount of energy. That's why stars shine. That's why nuclear reactions are so powerful. It is why the cosmos is bright at all. Without C, without the speed of light, there would be no bridge, no exchange, no life. The edge of motion. Imagine you are floating, not in water, not in air, but in something far stranger, a vast, silent ocean of space where there is no sound, no up or down, and no breath to warm your lips. Stars hang around you like scattered diamonds. Some burn bright and white. Others glow with a faint red sadness, and a few glitter blue like frost on midnight glass. You begin to drift forward. At first, it feels like swimming in slow motion. But here, in the absence of air or resistance, nothing slows you. Your body, tethered to no planet and no wind, continues gliding effortlessly. There is no friction to steal your energy. Every gentle push is carried forward forever. And yet, you notice something strange. The faster you go, the harder it becomes to imagine going faster still. Not because of muscles or fatigue, but because reality itself begins to whisper that there is a limit. That whisper is the speed of light. The idea that shocked the world. For most of human history, speed was something you could always imagine increasing. If a horse could run fast, a chariot might run faster. If a cannonball flew through the air, a bullet from a rifle could outpace it. And if ships cut through water with sails, steam engines could one day drive them quicker still. But then came the age of physics, and the first to truly put his ear to the heartbeat of light speed was not Einstein, but Ole Romer,
the 17th century Danish astronomer. With nothing but his eye, his mind, and Jupiter's moon Io, he realized light had a finite speed. It was not instant. Centuries later, James Clerk Maxwell, the Scottish physicist, gave us equations that not only described electricity and magnetism, but whispered a number, about 299,792 kilometers per second. The equation suggested light speed was not just fast, it was a cosmic constant. And then Einstein arrived. He didn't just accept light speed, he made it the foundation of reality. His theory of special relativity declared that nothing could outrun light, not even by the tiniest fraction of a second. What happens when you try? Imagine you are in a spaceship, sleek and silent, with engines capable of unimaginable thrust. You start slow, 10 kilometers per second, 100 kilometers per second, 1,000. Your body feels no resistance except the pressure of acceleration. The stars ahead of you begin to shift, crowding toward a single point, the center of your view. This is the relativistic aberration of light, space folding forward into a tunnel. You push faster. Time around you begins to stretch. The clock on your ship ticks normally for you, but as you glance at Earth through your instruments, its clocks seem to slow, like a movie played in molasses. This is not an illusion, it's time dilation. Push faster still, to 90% the speed of light, and the universe itself begins to protest. The energy needed to accelerate you grows wildly, no longer in a straight line, but in a steep, punishing curve. At 99.9% light speed, the mass your ship carries, from the universe's perspective, is no longer the mass it had at rest. It grows heavier in a sense, not because new atoms appear, but because your kinetic energy makes you behave as if you are more massive.
A story that begins long before you wake. The journey of sunlight is not as straightforward as it seems. When we think of the sun's light reaching us, we might imagine it leaving the sun's surface and racing across the void at 299,792 kilometers per second, the famous speed of light. And yes, once it escapes into space, that is exactly what happens. But the real story begins deep inside, in the sun's very heart, where the temperature soars to 15 million degrees Celsius. Here, hydrogen atoms are squeezed so tightly together that they fuse, becoming helium, releasing energy in the form of high-energy photons. These first photons are not the golden sunlight you know. They are gamma rays, invisible, blisteringly energetic, born in a place where pressure and heat defy imagination. And here's the part that still feels impossible. From the sun's core to its surface is only about 700,000 kilometers. If a photon could travel straight through, at the speed of light, it would make the trip in just over 2 seconds. But it doesn't. It can't. Instead, each newborn photon collides with atoms, is absorbed, released again, bounced around like a pinball in an endless, blinding arcade. It doesn't travel straight. It travels in chaos. 100,000 years for a few centimeters. Physicists estimate that it can take hundreds of thousands of years, perhaps even 1 million, for a single photon to finally work its way from the sun's core to the surface. Think about that. The sunlight touching your face this morning may have been born when early humans were painting animals on cave walls, when mammoths roamed icy plains, when no one yet dreamed of telescopes or spacecraft. In a way, sunlight is ancient before it ever meets the day. It carries not just heat and light,
but the deep memory of stars. The moment of escape. After its long and wandering birth, the photon finally reaches the sun's photosphere, a relatively cool layer compared to the core, a mere 5,500 degrees Celsius. Here, the photon escapes, and once free, it does something utterly different from its slow, staggering crawl inside the sun. It becomes a racer. In the vacuum of space, nothing hinders it. It moves at light speed, covering the 150 million kilometers to Earth in about 8 minutes and 20 seconds. No pause, no detour. A straight line across a darkness so complete that if the sun were suddenly to vanish, you would still see its glow for 8 precious minutes before night claimed the sky.
Humans learning the numbers. For most of history, people assumed that light moved instantaneously. Why wouldn't they? When you light a torch in the night, you see its glow immediately. When lightning strikes, the flash appears almost the same moment as the sound, except the sound is slower. It wasn't until the 1670s that a Danish astronomer, Ole Romer, gave humanity the first real evidence that light had a measurable speed. By studying the moons of Jupiter, he noticed their eclipses appeared to happen later when Earth was moving away from Jupiter and earlier when moving closer. From these delays, he calculated light speed, and though his number was not exact, it was astonishingly close to what we know today. Imagine the wonder. The universe, it turned out, was not instantaneous. There was a delay, a cosmic heartbeat between events and their appearance in our eyes. The sunlight that shapes us. The light that reaches Earth carries more than warmth. It writes the seasons, marks the days, feeds the plants whose green leaves turn photons into sugar, a quiet magic we call photosynthesis. It paints sunsets in burning gold and blush pink. It makes rainbows possible. Even our sleep, our mood, our very biology is tied to this daily rhythm of light and shadow. Ancient civilizations worshipped the sun as a god because they knew, without equations, that without it, nothing would live. The silence of the journey. When we speak of light crossing space, it's easy to forget the vast silence it travels through. There is no sound in space, no breeze, no resistance. The photon leaves the sun's surface, and in those 8 minutes of flight, it passes Mercury's scorched world, glances by Venus shrouded in clouds, and approaches Earth, a small blue and white marble, turning slowly in the dark. When it strikes the atmosphere, some light is scattered, some absorbed, some reflected back to space, but some, perhaps the one destined for you, enters your eye, touches your retina, and is transformed into an electrical signal that your brain interprets as sight. That's the end of its long, unimaginable journey, from the heart of a star to the spark of perception in a human mind.
This is the wall that nature has built. The cosmic speed limit is not just about light. It's tempting to imagine the limit as a cosmic police officer wagging a finger and saying, "No faster than 299,792 kilometers per second, young traveler." But it's not a law written on a page. It's the way space-time itself is built. Light is not fast simply because it's energetic. It's fast because it has no rest mass. A photon is a ripple in the electromagnetic field, born already at the speed limit. Nothing needs to push it to that speed. It simply exists there. Everything else, from grains of dust to colossal stars, carries mass, and with mass comes a kind of gravitational tether to space-time. The faster you try to go, the tighter that tether pulls back,
not with a rope, but with the bending of time and the stretching of energy. And so, no matter how mighty your engines or how desperate your wish, the edge of motion remains unreachable. Philosophy of the limit. Why should the universe have such a barrier? Is it an act of cruelty or of mercy? Without a speed limit, causality, the link between cause and effect, could shatter. Signals could arrive before they were sent. A bullet could hit before the trigger was pulled. Time itself could fold into paradox. The limit preserves order. It keeps past and future from blending into chaos. It is the thread that stitches events into a coherent tapestry. And yet, within this boundary, the universe allows us something wondrous. Though we cannot exceed light speed, we can manipulate the way we experience time. A traveler near light speed may live only a year while centuries pass elsewhere. Ships might cross galaxies in what feels like months, while homeworlds age beyond recognition. The speed limit shapes the universe, but within it lies a strange kind of freedom. The quiet wonder of light. And so here you float again in your mind's ship, staring at the endless black. You know now that light is not simply fast, it is fundamental. It is the pulse by which the universe keeps time. It is the rhythm to which every atom dances. If you close your eyes, you might even imagine hearing it, not as a sound, but as a silent hum that exists in the space between seconds. In the end, the speed of light is not a wall to be resented, but a horizon to be admired. It is the edge of motion, the point where our understanding bows to the elegance of nature. And perhaps one day when humanity learns to fold space itself, we will find ways to cross vast distances without ever breaking that sacred limit. But until then, light remains the fastest messenger, the eternal runner across the cosmic sea. The daylight messenger, how the sun's light travels to us. Imagine the sun, not the flat yellow circle you see drawn in a child's book, but the real one, a roiling sphere of fire, so vast that more than 1,000,000 Earths could fit inside. It is not silent, though you cannot hear it. It hums in a language of charged particles. It whispers in the vibrations of magnetic storms, and it breathes out a constant wind. And every morning, or more precisely, 8 minutes and 20 seconds before your morning, a messenger begins a journey from the heart of that star, destined for your eyes.
Whenever you see that C, know that it's not just a number. It is the cosmic conversion rate between the stuff of the universe, mass, and the fire of the universe, energy. And because C is so enormous, 300 million meters per second, even a tiny bit of mass contains an astonishing amount of energy. That's why stars shine. That's why nuclear reactions are so powerful. It is why the cosmos is bright at all. Without C, without the speed of light, there would be no bridge, no exchange, no life. The edge of motion. Imagine you are floating, not in water, not in air, but in something far stranger, a vast, silent ocean of space, where there is no sound, no up or down, and no breath to warm your lips. Stars hang around you like scattered diamonds. Some burn bright and white, others glow with a faint red sadness, and a few glitter blue like frost on midnight glass. You begin to drift forward.
At first, it feels like swimming in slow motion. But here, in the absence of air or resistance, nothing slows you. Your body, tethered to no planet and no wind, continues gliding effortlessly. There is no friction to steal your energy. Every gentle push is carried forward forever. And yet, you notice something strange. The faster you go, the harder it becomes to imagine going faster still. Not because of muscles or fatigue, but because reality itself begins to whisper that there is a limit. That whisper is the speed of light. The idea that shocked the world. For most of human history, speed was something you could always imagine increasing. If a horse could run fast, a chariot might run faster. If a cannonball flew through the air, a bullet from a rifle could outpace it. And if ships cut through water with sails, steam engines one day could drive them quicker still. But then came the age of physics, and the first to truly put his ear to the heartbeat of light's speed was not Einstein, but Ole Romer, the 17th century Danish astronomer. With nothing but his eye, his mind, and Jupiter's moon Io, he realized light had a finite speed. It was not instant. Centuries later, James Clerk Maxwell, the Scottish physicist, gave us equations that not only described electricity and magnetism, but whispered a number, about 299,792 kilometers per second. The equations suggested light speed was not just fast, it was a cosmic constant. And then Einstein arrived. He didn't just accept light speed, he made it the foundation of reality. His theory of special relativity declared that nothing could outrun light, not even by the tiniest fraction of a second. What happens when you try? Imagine you are in a spaceship, sleek and silent, with engines capable of unimaginable thrust. You start slow, 10 kilometers per second, 100 kilometers per second, 1,000. Your body feels no resistance except the pressure of acceleration. The stars ahead of you begin to shift, crowding toward a single point, the center of your view. This is the relativistic aberration of light, space folding forward into a tunnel. You push faster. Time around you begins to stretch. The clock on your ship ticks normally for you, but as you glance at Earth through your instruments, its clocks seem to slow, like a movie played in molasses. This is not an illusion. It's time dilation. Push faster still, to 99% light speed, and the universe itself begins to protest. The energy you need to accelerate you grows wildly, no longer in a straight line, but in a steep, punishing curve. At 99.9% light speed, the mass your ship carries from the universe's perspective is no longer the mass it had at rest. It grows heavier in a sense, not because new atoms appear, but because your kinetic energy makes you behave as if you are more massive. Push again to 99.9%, and your engines scream. You pour more and more power into your motion, yet your speed inches upward more and more slowly. The energy you require now is like trying to move a mountain with every breath. Whenever you see that C, know that it's not just a number. It is the cosmic conversion rate between the stuff of the universe, mass, and the fire of the universe, energy. And because C is so enormous, 300 million meters per second, even a tiny bit of mass contains an astonishing amount of energy. That's why stars shine. That's why nuclear reactions are so powerful. It is why the cosmos is bright at all. Without C,
Without this speed of light, there would be no bridge, no exchange, no life. The edge of motion. Imagine you are floating, not in water, not in air, but in something far stranger, a vast, silent ocean of space, where there is no sound, no up or down, and no breath to warm your lips. Stars hang around you like scattered diamonds. Some burn bright and white, others glow with a faint red sadness, and a few glitter blue like frost on midnight glass. You begin to drift forward. At first, it feels like swimming in slow motion, but here, in the absence of air or resistance, nothing slows you. Your body, tethered to no planet and no wind, continues gliding effortlessly. There is no friction to steal your energy. Every gentle push is carried forward forever. And yet, you notice something strange. The faster you go, the harder it becomes to imagine going faster still. Not because of muscles or fatigue, but because reality itself begins to whisper that there is a limit. That whisper is the speed of light. The idea that shocked the world. For most of human history, speed was something you could always imagine increasing. If a horse could run fast, a chariot might run faster. If a cannonball flew through the air, a bullet from a rifle could outpace it. And if ships cut through water with sails, steam engines one day could drive them quicker still. But then came the age of physics, and the first to truly put his ear to the heartbeat of light's speed was not Einstein, but Ole Romer, the 17th century Danish astronomer. With nothing but his eye, his mind, and Jupiter's moon Io, he realized light had a finite speed. It was not instant. Centuries later, James Clerk Maxwell, the Scottish physicist, gave us equations that not only described electricity and magnetism, but whispered a number, about 299,792 kilometers per second. The equations suggested light speed was not just fast, it was a cosmic constant. And then Einstein arrived. He didn't just accept light speed, he made it the foundation of reality. His theory of special relativity declared that nothing could outrun light, not even by the tiniest fraction of a second. What happens when you try? Imagine you are in a spaceship, sleek and silent, with engines capable of unimaginable thrust. You start slow, 10 kilometers per second, 100 kilometers per second, 1,000. Your body feels no resistance except the pressure of acceleration. The stars ahead of you begin to shift, crowding toward a single point, the center of your view. This is the relativistic aberration of light, space folding forward into a tunnel. You push faster. Time around you begins to stretch. The clock on your ship ticks normally for you, but as you glance at Earth through your instruments, its clocks seem to slow, like a movie played in molasses. This is not an illusion. It's time dilation. Push faster still, to 99% light speed, and the universe itself begins to protest. The energy you need to accelerate you grows wildly, no longer in a straight line, but in a steep, punishing curve. At 99.9% light speed, the mass your ship carries from the universe's perspective is no longer the mass it had at rest. It grows heavier in a sense, not because new atoms appear, but because your kinetic energy makes you behave as if you are more massive. Push again to 99.9%, and your engines scream. You pour more and more power into your motion,
yet your speed inches upward more and more slowly. The energy you require now is like trying to move a mountain with every breath.
Humans learning the numbers. For most of history, people assumed that light moved instantaneously. Why wouldn't they? When you light a torch in the night, you see its glow immediately. When lightning strikes, the flash appears almost the same moment as the sound, except the sound is slower. It wasn't until the 1670s that a Danish astronomer, Ole Romer, gave humanity the first real evidence that light had a measurable speed. By studying the moons of Jupiter, he noticed their eclipses appeared to happen later when Earth was moving away from Jupiter and earlier when moving closer. From these delays, he calculated light speed, and though his number was not exact, it was astonishingly close to what we know today. Imagine the wonder. The universe, it turned out, was not instantaneous. There was a delay, a cosmic heartbeat between events and their appearance in our eyes. The sunlight that shapes us. The light that reaches Earth carries more than warmth. It writes the seasons, marks the days, feeds the plants whose green leaves turn photons into sugar, a quiet magic we call photosynthesis. It paints sunsets in burning gold and blush pink. It makes rainbows possible. Even our sleep, our mood, our very biology is tied to this daily rhythm of light and shadow. Ancient civilizations worshipped the sun as a god because they knew, without equations, that without it, nothing would live. The silence of the journey. When we speak of light crossing space, it's easy to forget the vast silence it travels through. There is no sound in space, no breeze, no resistance. The photon leaves the sun's surface, and in those 8 minutes of flight, it passes Mercury's scorched world, glances by Venus shrouded in clouds, and approaches Earth, a small blue and white marble, turning slowly in the dark. When it strikes the atmosphere, some light is scattered, some absorbed, some reflected back to space, but some, perhaps the one destined for you, enters your eye, touches your retina, and is transformed into an electrical signal that your brain interprets as sight. That's the end of its long, unimaginable journey, from the heart of a star to the spark of perception in a human mind. Philosophy in the shadows. The cosmic lighthouse gives us both beauty and melancholy. It tells us that the universe is vast, ancient, and filled with wonders beyond our imagining, but it also reminds us of our limits. There will always be places we cannot go, sights we cannot see, and truths we cannot know. For some, this is frustrating. For others, it is comforting. The limits draw the frame for the picture. Without them, there would be no shape to the story, no boundaries for meaning to take root. Perhaps the cosmic lighthouse is not a prison, but a stage, and we, as the audience, watch the light sweep across the darkness, catching glimpses of the great cosmic drama before the beam moves on. When the universe became a clock. It was a gray morning in Paris, 1676. The bells of Notre Dame rang faintly in the distance, their sound moving through the air far slower than the light that bathed the cathedral spires. In the quiet study of the French Academy of Sciences, Ole Romer, a Danish astronomer with calm, piercing eyes, was making the final ink strokes on a set of numbers that would shake the very foundation of how humans thought about the heavens. Romer had been obsessed with Jupiter's moon Io, not for its beauty, but for its punctuality. Each time Io passed behind Jupiter, it vanished from sight, like clockwork. But after years of observation, Romer noticed something troubling. The clock wasn't perfect. Sometimes Io seemed late, sometimes early. The difference was small, but in the world of astronomy, small differences whispered of great truths.
Most astronomers blamed faulty instruments or the imperfect hands of man, but Roemer's instincts told him otherwise. He saw a pattern, the delays lined up with Earth's position in its orbit. When Earth was moving away from Jupiter, Io's eclipse appeared late. When Earth was moving closer, it appeared early. Roemer's mind turned these observations over and over until a single audacious thought emerged. Light does not move instantly. This was heresy to many. Since ancient Greece, most had believed that light appeared the instant it was created. Aristotle thought of it as an immediate property of the eye. Descartes, just a generation earlier, had defended the idea that light's transmission was instantaneous. The heavens, after all, were supposed to be perfect, and perfection was not slow. But Roemer dared to measure the imperfection. Using his meticulous tables, he calculated that light took about 22 minutes to cross the diameter of Earth's orbit. From this, he estimated the speed of light to be roughly 214,000 kilometers per second. Not exact by modern standards, but breathtakingly close for a man using nothing more than a telescope, patience, and his mind. The news spread through Europe like a whisper of lightning. The idea that light had a finite speed, that it took time to travel, transformed it from a mystical instant into something measurable, something that could be plotted, predicted, and used. For the first time, humanity began to see light not just as illumination, but as a messenger bound by the laws of the universe. The universe as a timekeeper. If light had a speed, then the universe had a delay, a kind of built-in echo. When you looked at Jupiter, you weren't seeing it now, but tens of minutes ago. This realization was like opening a secret door in the mind. The cosmos was not happening all at once. Every star, every planet, every galaxy existed for us in the past. From that moment, astronomy changed. Telescopes were no longer just instruments of sight, they became time machines. Every observation carried a timestamp written in the language of light. Generations of scientists would carry Roemer's seed of an idea forward. James Bradley, in 1728, noticed the phenomenon of stellar aberration, a tiny shift in starlight caused by Earth's motion through space, and confirmed the finite speed of light again. By the mid-19th century, French physicist Hippolyte Fizeau had devised a spinning-toothed wheel experiment to measure light speed on Earth, refining the number even further. But it was in the late 19th century that something stranger began to emerge, something that would turn the speed of light from a fact into a law. Maxwell's equations and the pulse of reality. James Clerk Maxwell was not an astronomer, but a Scottish physicist with a gift for seeing unity where others saw fragments. By the 1860s, he had developed a set of equations that described electricity and magnetism as two faces of the same coin. When he worked through the math, he found something extraordinary. The equations predicted the existence of waves that traveled at a constant speed. When Maxwell calculated that speed, he nearly dropped his pen. The number matched the measured speed of light. This was more than coincidence. It meant light was not just a phenomenon of sight, it was an electromagnetic wave, born from the dance of electric and magnetic fields. And these waves didn't need air, water, or any medium at all to travel. They were woven into the very structure of the universe. But there was something even stranger. Maxwell's equations gave the same number no matter the motion of the source or the observer. Whether you chased the wave or ran from it, it came at you with the same speed. Light, it seemed, was stubborn.
It wasn't until the early 20th century that this speed became something far more mysterious, something fundamental. In 1905, Albert Einstein proposed a radical idea. No matter how fast you are moving, if you measure the speed of light, you will always get the same answer. If you run toward a beam of light or away from it, you don't make it approach you faster or slower. It remains constant. This was unlike anything else in nature. If you run toward a ball someone throws, it reaches you quicker. If you run away, it takes longer. But light, it does not play by those rules. And so began the strange logic of relativity.
Why the universe needs a speed limit. At first glance, this speed limit seems arbitrary. Why would nature care? But think about what happens when you try to push an object faster and faster. As your speed increases, your energy requirements grow, not steadily, but explosively. Near the speed of light, your energy needs climb toward infinity, and infinity is, well, impossible. The universe is not cruel for setting this limit. It is merciful. Without this limit, cause and effect would crumble. Events could reverse order. Time could twist and knot. The universe might collapse into paradox, a place where the past and future are tangled beyond repair. The human longing to break it. Yet, as humans, we do not like boundaries. Tell us, you can't. And we ask, but what if? Writers dream of warp drives and wormholes. Physicists imagine hypothetical particles called tachyons, faster than light travelers. We know these may be fantasy, yet the longing persists. Why? Because the speed of light is not merely about light. It is about the structure of space and time itself. In Einstein's universe, light's speed is the sewing thread that stitches space and time together into one fabric. Remove it, and the whole tapestry unravels. It is as if the cosmos itself has written its most sacred law in the language of light. This is the fastest anything can go. Beyond this, time itself changes meaning. Reflections beneath the stars. So, when you stand outside on a clear night and gaze at the stars, remember, the light that touches your eyes has traveled years, centuries, even millennia to reach you. It has obeyed the limit, faithfully carrying the story of distant suns without ever breaking the law. It is a humble messenger, never rushing, never slowing. And in its quiet, constant journey, there is a lesson for us. The Sea of Darkness. Imagine you are standing on the deck of a ship at midnight. The air is cold, sharp, and clean. The ocean is black as liquid obsidian, stretching endlessly in all directions. Above, the stars look close enough to touch, pinpricks of silver light scattered like ancient jewels on the dark velvet of the sky. The ship creaks. The waves lap gently against the hull. Somewhere in the distance, a lone gull calls into the night, but its voice is swallowed by the vastness. Now, imagine you are not just standing here. Imagine you are moving, not through water, but through the very fabric of space itself. Imagine the sea beneath you is the infinite void, and you are sailing at unimaginable speed, faster than any ship, any bullet, any thought. But you are still nowhere near the speed of light. The dream of the infinite sailors. For thousands of years, humanity has been like this ship, adrift in the cosmic sea. The sailors of old had their horizons, and their horizons were small. They thought the sea ended somewhere, that if you sailed far enough, you might fall into nothing. They could not imagine oceans without end. In the same way, early thinkers could not imagine that the universe might be so vast, so boundless, that even light, this thing so swift, so divine, so pure, might take centuries to cross it. The first to truly dream of measuring light's speed were like sailors who dared to leave sight of the shore. They wanted to know, how far does the sea of darkness go, and how fast can we sail it? The Night Watchers. One such cosmic sailor was Ole Romer in the late 1600s. He did not have a telescope that could pierce galaxies. He did not have radio dishes or satellites. He had his eyes, the moons of Jupiter, and an unshakable patience. Night after night, he watched Io, one of Jupiter's moons, drift behind the planet and reappear. He measured the moments with a clock, again and again for months. But he noticed something strange. The timing was changing. When Earth was moving toward Jupiter, Io appeared sooner. When Earth was moving away, Io appeared later. It was as if the light from Io was arriving on a delayed ship carried across the cosmic sea. From this, Romer deduced something profound. Light takes time to travel. It is not instant. It is not a godlike blink that fills the universe in a heartbeat. It is fast, yes, unimaginably so, but not infinite. The sea has currents. The sea has limits. The black compass. For sailors at sea, a compass points the way. But for those who sail the cosmic ocean, the compass is light itself. It shows us where things are, how far they are, and how they move. Without light, there is no map, no position, no navigation. We would be like blind sailors drifting through a void without knowing there even was a void. That is why the speed of light is more than just a number. It is the heartbeat of the universe's navigation system. It is the measure by which all distances are known. A light year, the distance light travels in a year, is the universe's own ruler, carved into the very fabric of reality. The unreachable shore. If you were a sailor on Earth in the 1400s, your unreachable shore might be the edge of the known world. If you are a cosmic sailor today, your unreachable shore is anything beyond the speed of light. This is the hardest truth for many to accept. No matter how perfect your ship, no matter how fierce your sails, no matter how brave your crew, you will never cross that barrier. The speed of light is the wind limit of the cosmic ocean. Push harder, and you do not move faster. You simply change the nature of your journey. Time itself begins to bend. And that is perhaps the strangest, most beautiful part of all. The closer you sail to light speed, the slower your own time flows compared to the universe around you. You could leave Earth, travel near the speed of light for what feels like a few years, and return to find centuries have passed. Your ship would not just sail through space, it would sail into the future, the endless night. But there is a melancholy to this sea. You could travel for 100,000 years, and still the light from distant galaxies would not yet have reached you. The universe is so vast that even light, our fastest sailor, is still on its journey to bring us news from the farthest shores. We live in a constant present made from ancient light. When we look at the stars, we are not seeing them as they are, but as they were. The light from some may have traveled for millions of years before touching our eyes. It is a bittersweet truth. The universe's messages are beautiful, but they are always late.
The quiet understanding. And so, the sailors of the cosmic sea, the scientists, the dreamers, the poets, have learned something. If you cannot outrun the wind, you learn to read it. If you cannot reach the unreachable shore, you learn to love the journey. The speed of light is not a prison. It is a promise that the universe will always have mystery, that there will always be horizons worth chasing. The Black Sea will never be fully crossed, but that is what keeps our ships ready, our maps open, and our hearts curious. In the end, as you stand on that midnight deck and watch the starlight glimmer on the endless water, you understand. You are already a sailor in the greatest ocean there is. Your journey began long before you knew it, and it will go on long after you are gone. And somewhere, out there, the light continues to sail, swift, steady, and eternal. The Great Light Debates. Imagine you were seated in a vast wooden hall, the air heavy with the smell of ink and parchment, where the faint golden glow of oil lamps trembles in the draught. The year is 1676. Outside, the cobblestone streets are slick from an evening rain. Inside, scholars in long coats and powdered wigs sit in small circles, voices low but urgent. Their topic is not war, not politics, not trade, but light. Light, in all its mystery, has become the battleground of the mind. It is easy for us now, in the 21st century, to think of light as something measured, catalogued, and understood. We speak of the speed of light, as if it were a constant carved into the very fabric of the universe, a neat figure printed in a physics textbook. But in the 17th century, light was an enigma. Was it instantaneous, moving with infinite speed, or did it, like a horse or a cannonball, take time to travel from one place to another? This was not an idle question, for if light had speed, then perhaps the universe itself could be measured in ways no one had imagined before. Ola Romer's Quiet Revolution. Enter Ola Christensen Romer, a Danish astronomer with the kind of patient curiosity that history often forgets to honor. He was not a man of loud proclamations or theatrical gestures. Instead, he had a gift for sitting quietly in the cold night air, peering through the eyepiece of a telescope, waiting for the right moment. His object of study was not light itself, but Jupiter's moon, Io. Every time Io passed behind Jupiter, disappearing into its shadow, Romer marked the time. Like a clockwork, the moon would reappear, a celestial heartbeat. But over months of careful observation, Romer noticed something strange. Sometimes Io appeared later than predicted, sometimes earlier. He wondered what could possibly cause such delays. Could the mechanics of the heavens themselves be flawed? Then it struck him. The Earth's orbit was not a stationary point. It moved around the sun. When Earth was moving away from Jupiter, light from Io had farther to travel and thus arrived later. When Earth was moving toward Jupiter, the opposite happened. With this quiet, almost poetic reasoning, Romer became the first human to estimate the speed of light. His number was not precise by modern standards, but it shattered the old belief that light's speed was infinite. It was a moment of intellectual courage, changing not just a number, but the very way we think about the universe. Debates and doubts. But revolutions in thought do not happen without resistance. In the coffee houses of London and the lecture halls of Paris, Romer's claim became the subject of fiery debate. How could something as swift as light, something that seemed to appear instantly, be slowed down by any measure? Some insisted the delay was an illusion. Others feared that to admit light had a finite speed was to open the door to dangerous questions. If light took time to travel, did that mean we never saw the universe as it truly was, but only as it had been? Did the heavens we gazed upon belong to the past? And if so, what did that mean for the notion of divine perfection? That the heavens were eternal, unchanging, and present to us in all their glory. In those days, ideas carried a different weight. They were not simply abstract concepts tossed about for curiosity's sake. They touched upon religion, philosophy, and humanity's place in the cosmos. I imagine Romer walking home from the observatory on a winter night, his breath clouding in the freezing air, feeling the enormity of his conclusion. He was not merely measuring a number, he was measuring the gap between reality and perception. Perhaps he paused to look at the flicker of a lantern in the distance, thinking, even this small light, this humble flame, is not here in the moment I see it. It has already left the source.
I am forever chasing it. Forever, a fraction of a second behind.
The unseen future in the past's light. We tend to think of history as a chain of events, but the discovery of light's finite speed was a kind of time travel. Suddenly, every star became a messenger from the past. The sun itself was not now, but 8 minutes ago. The nearest stars? Years old in our eyes. The farthest galaxies? Billions of years removed from the moment we stand in. What Romer glimpsed, perhaps without realizing it, was that the night sky is not a picture of the present. It is a vast, glittering archive. The speed of light is the great cosmic editor, deciding what moments we are allowed to see and when. It is one of the most humbling ideas in science, and it began not with massive laboratories or computers, but with one man and his careful, patient gaze. Why this matters today? The debates that began in that dimly lit hall in the 17th century still echo in our own age. When we speak of the speed of light today, we are not just stating a number, 299,792,458 meters per second, we are acknowledging that we live in a universe with boundaries, not of walls or fences, but of time. Every photograph taken by a space telescope, every burst of light from a distant quasar, is not a look into the present moment, but into the pages of a history that light has been writing for eons. When we see a galaxy a billion light years away, we are peering into a moment that happened long before the Earth even existed. And when future civilizations look back at our own little blue planet, they too will see a version of us that no longer is. The lamps in the old hall have long been extinguished. The cobblestones are gone, the rain has dried, the debates have moved from parchment to digital screens. But the truth Romer uncovered remains, as constant and unyielding as the speed of light itself. We are all living in the past. Every star you see tonight is a memory. And perhaps, so are you. The Prism and the Poet. The year is 1666, and the summer air of Woolsthorpe is heavy with the smell of rain-soaked grass. A young man, quiet, inward-looking, and pale from long hours indoors, sits at his wooden desk, a beam of sunlight cutting across the dusty air in front of him. His name is Isaac Newton. Outside, the world is restless with plague, politics, and war, but inside his small study, there is only the hush of paper and the glint of glass. On the desk lies an object as ordinary as it is extraordinary, a triangular prism, cool and smooth in the hand, its edges catching the light like a frozen fragment of a rainbow. He lifts it, holding it in the path of the sunbeam. What happens next will change our understanding of light forever. The beam passes through the prism and bursts, explodes into color. Reds, oranges, yellows, greens, blues, indigos, violets. A perfect spectrum splays itself onto the far wall, shimmering like a secret finally told. The colors are pure, sharper than any painter's pigment, as if the sun itself had spilled its hidden soul into Newton's studio. He begins to experiment. He darkens the room, punching a small hole in the window shutter to allow just one beam to enter. He places the prism in the beam's path, observing the spectrum. Then carefully, he lets just one color pass through a second prism. Instead of breaking further apart, it remains pure. Red stays red. Blue stays blue. This means that colors are not made by the prism, they are already inside the light. As night falls, Newton sits by candlelight, sketching diagrams of beams, angles, and colors. His hand moves with a quiet rhythm, the quill whispering over parchment. He knows he's glimpsing a deeper truth, but he also knows the world may not be ready to hear it. Many scholars will resist the idea that light is a blend of colors. After all, it goes against the wisdom of centuries. But Newton has seen the evidence with his own eyes, and once the truth has been seen, it cannot be unseen. The prism experiments will become a cornerstone of optics, laying the groundwork for centuries of discoveries. From this, scientists will begin to understand light as both a wave and, much later, a particle. They will measure its speed, study its bending, and eventually realize that it has a limit, a cosmic speed limit that even thought experiments cannot break.
Yet there's also something deeply poetic here. Newton didn't just measure light. He revealed its secret inner life. He showed that within what seems plain and simple, there can be infinite richness waiting for the right moment to emerge. It is a reminder, perhaps, that truth is often hidden in plain sight, waiting for a curious mind to look closer. Outside, the rain stops. The last light of day glows across the countryside, gilding the edges of the leaves. Newton's prism lies on the desk, still faintly warm from the sun. Somewhere in that glass, a spectrum sleeps, ready to awaken at the next touch of light. And so the story of light continues, not only in laboratories, but in the quiet rooms of poets, painters, dreamers, and those who still believe that the simplest beam can hold the most beautiful mysteries. The cosmic speed limit and the whispering edge of the universe. Imagine a night so still that you can hear your own breath. The air is cool, not cold, the kind that feels like silk against your skin. You step outside, far away from the hum of cities, and overhead the stars scatter themselves like tiny windows into eternity. For a moment, your eyes adjust to the dark, and then there it is, the faint, barely perceptible arc of the Milky Way, a pale river of light stretching from one end of the horizon to another. Every speck of light above you, every single one, took time to arrive. Some of those photons began their journey when ancient civilizations were just learning how to write. Others began before there were even humans to see them. And that's the quiet, astonishing truth about the speed of light. It's not just a number written in physics books. It's the boundary between now and the past. It is, in a sense, the ruler by which the universe measures distance and time. The edge that isn't an edge. Scientists talk about something called the observable universe, the farthest distance from which light has had time to reach us since the beginning of everything. It's tempting to imagine this as a wall or a black curtain out there in space, but it's not. It's not an edge you can touch or cross. It's more like the limit of a story you've been able to read so far. Beyond that limit, more story exists, but the cosmic ink hasn't yet had time to flow to your page. Right now, that observable boundary lies roughly 46 billion light-years away in every direction. This is far larger than the universe was at the time the light was emitted. Because while that light was on its way, the universe itself kept expanding. And yet, no matter how powerful our telescopes, nothing can show us beyond that cosmic horizon. The speed of light draws an invisible curtain, whispering, "Not yet."
The gentle dictator. The speed of light, 299,792 kilometers per second, is often spoken of as a cold fact of physics. But there's a strange elegance to it. It's not a cruel jailer that limits us out of spite. It's more like a wise guardian, ensuring that cause always comes before effect, that the universe has a rhythm that can be trusted. Without this cosmic limit, the sequence of events could dissolve into chaos. Messages could arrive before they were sent. Effects could appear before their causes. History could unravel. This speed limit is the silent architecture of reality, and the more we study it, the more it feels protective. Not in a sentimental way, but in the same way a heartbeat is protective, in the way it keeps life's rhythm steady. The time traveler's paradox. Here's the part that feels like a bedtime riddle. When you look far enough into space, you're not looking into distance, you're looking into time. If you point a telescope at the Andromeda galaxy, the light entering your eye tonight left there 2.5 million years ago. That means you're seeing Andromeda not as it is now, but as it was before humans even existed on Earth.
Look further, and you begin to see galaxies as they were billions of years ago, when they were young, chaotic, and full of raw energy. Push further still, and the view becomes stranger, until you reach the faint afterglow of the Big Bang itself. That afterglow is called the cosmic microwave background, light that has been traveling for 13.8 billion years, ever since the first atoms formed. It is the oldest light we can see, a baby picture of the universe. And beyond that, silence. Not because nothing is there, but because light from beyond that point simply hasn't reached us yet. The poetry of waiting. In a strange way, the speed of light teaches patience. It reminds us that some stories can't be rushed, that some answers, whether about the universe or our own lives, arrive only when the time is right. The stars overhead are patient storytellers. Some have been shining toward us for eons, their photons crossing gulfs of darkness without hurrying, without pause. And when they finally reach your eye, you become the last chapter of their journey. You, standing there under the night sky, are where the light ends. It began billions of years ago, and it ends with you, here, now, breathing quietly in the dark. Closing your eyes. Tonight, as you close your eyes, imagine the universe not as an endless expanse, but as a great slow tide of light forever rolling towards you. Every second, ancient beams arrive, carrying messages from when galaxies were infants, from when space itself was young. And beyond your reach, beyond your sight, more light is on its way. The cosmic speed limit may mean we cannot see it yet, but that only means the story isn't finished. The next chapters are still traveling, still coming, still finding their way to you.
Time under question. By the turn of the 20th century, the stubbornness of light had become a problem. The prevailing belief was that all waves needed a medium to travel through. For sound, it was air. For ocean waves, water. For light, the theorized luminiferous aether. The aether was supposed to be an invisible, undetectable sea filling the universe. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to detect the aether by measuring the speed of light in different directions. If Earth moved through this medium, the speed of light should change slightly depending on whether you measured it along or against the aether wind. The result was devastating to the theory. No difference at all. Light always moved at the same speed, no matter what. It was a quiet catastrophe in physics. If light didn't change its speed, then the universe's rules were stranger than anyone imagined. Time and space themselves would have to bend to make the numbers work. Einstein and the cosmic clock. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies. In it, he did something bold. He declared that the speed of light in a vacuum was the same for all observers, no matter how they moved. Instead of bending light to fit our understanding of time and space, he bent time and space themselves. The result was special relativity, a theory in which time slows down and distances shrink for objects moving close to light speed. Light became not just a wave or a particle, but a cosmic speed limit, a built-in constraint on the universe's flow of events. Suddenly, Romer's old observation about Io wasn't just an astronomical curiosity, it was a clue to the deepest structure of reality. The universe wasn't just a stage on which events unfolded. It was a clock, and light was its ticking hand. The human side of the clock. From ancient firelight to Romer's telescope, from Maxwell's equations to Einstein's relativity, humanity had learned to measure time not just in seconds, minutes, and hours, but in light years, the distance light travels in 1 year. It was a poetic transformation. Our calendars measured our lives. The stars measured our place in the cosmos. The light from Proxima Centauri, the nearest star beyond the sun, took more than 4 years to reach us. The Andromeda Galaxy's light began its journey when early humans were still learning to paint in caves.
every beam of light carried a date, and that meant every glance at the night sky was a reunion with the past. The next episode, episode 23, The Daylight in the Dark, will follow how this understanding changed the way we searched the universe, leading to the great age of cosmic exploration. The Great Cosmic Speed Limit, a law written in light. Imagine, if you will, the vastness of a cosmic ocean. No horizon, no shore, just an endless sea of black velvet, flecked with the faint shimmer of distant suns, like diamonds scattered on a jeweler's cloth. Now imagine you are a voyager in this ocean. You have the most magnificent ship, not of wood or steel, but of pure thought and ambition. You want to sail faster than anything has ever sailed before. You want to chase the glimmering stars themselves. And then, a voice. Not from the heavens, not from the earth, but from the very laws of nature. Whispers, no further, not faster. This is the limit. The discovery of a boundary. The idea that nothing can move faster than light did not come to us all at once. It was not a decree handed down by ancient philosophers, nor a proclamation carved into stone. It was born slowly, through centuries of questions. Questions like, how far is the sun? How fast does light travel? Is there anything swifter? The ancient Greeks thought light was instantaneous. To them, its travel was too quick to measure. They saw the lightning flash and the thunder rumble later, and they knew sound was slower, but light seemed eternal and immediate. Then came the first great cracks in that assumption. In 1676, a Danish astronomer named Ole Romer was studying Jupiter's moons. He noticed something strange. The eclipses of Io, one of Jupiter's moons, didn't happen exactly when they were predicted. Sometimes they were late, sometimes early. The explanation? Light was fast, but not infinite. It traveled at a measurable speed, a staggering 186,000 miles per second, about 300,000 kilometers per second. The number was so immense that for most practical purposes, it still felt like infinity, but it was not. The strangest law of all. For centuries after Romer's discovery, scientists treated the speed of light as simply a very large number, a constant for calculations, a piece of trivia in physics textbooks.